On September 18, 2025, two seemingly impossible things happened within 72 hours of each other. Russia's Kamchatka peninsula shook with a magnitude 7.8 earthquake, the latest in a devastating sequence that began in July. But 3 days earlier, our planet was also hit by a G3 geomagnetic storm as our sun awakened from an 11-year slumber. Coincidence? Perhaps. But there's a third player in this cosmic drama. 3I Atlas, the interstellar visitor currently hurtling toward our star with a plasma coma half the size of the sun itself and growing bigger every single day. For better or for worse, we are witnessing something that has never been observed in recorded history. Stay with me on tonight's exploration as we unravel whether these extraordinary events represent random chance or something far more interconnected than science dares to admit. Part 1. The Sun is Waking Up. On September 18, 2025, the Earth shuddered. A magnitude 7.8 earthquake ripped through the waters off Russia's Kamchatka peninsula, sending tremors across the Pacific Ring of Fire. But here's what makes this moment extraordinary. Just 3 days earlier, our planet had been hammered by something else entirely. A G3 geomagnetic storm, one of the most powerful space weather events of the year, had swept through our magnetosphere like an invisible tsunami. 2 events, 1 weekend, and sitting between them, a question that would make any rational scientist pause. What are the odds? You see, our sun is waking up. After years of relative quiet, solar cycle 25 is reaching its peak, and the numbers tell a story that's both fascinating and unsettling. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center has been tracking increased activity, more coronal holes, high-speed solar wind streams, and geomagnetic disturbances that can light up auroras as far south as Colorado. But here's where things get interesting. That September 14th through 15th G3 storm didn't come from a solar flare or a coronal mass ejection. It came from something more subtle, more persistent, a coronal hole high-speed stream. Imagine the sun's magnetic field lines opening up like a flower, creating a highway for charged particles to race toward Earth at speeds exceeding 600 kilometers per second. The earthquake that followed was no ordinary aftershock either. This 7.8 magnitude event struck the same region that had been devastated just 7 weeks earlier by an 8.8 magnitude monster, one of the most powerful earthquakes ever instrumentally recorded. The July 29th event had triggered Pacific-wide tsunami warnings, with detection systems from Hawaii to Chile monitoring waves that could reshape coastlines. Now, any seismologist worth their degree will tell you that earthquakes are driven by tectonic forces, the slow, grinding dance of continental plates that has been choreographing our planet's surface for billions of years. And they're absolutely right. But what if there's more to the story? Enter our third actor in this cosmic drama, 3I Atlas, officially designated C/2025N1. This isn't just any comet. It's our solar system's third confirmed interstellar visitor, a traveler from the void between stars that's currently hurtling toward a close encounter with our Sunday. On October 30th, 2025, it will reach perihelion, its closest approach to our star, at a distance of roughly 1.4 astronomical units. Before you start stockpiling canned goods, let me be clear. 3I Atlas poses absolutely no threat to Earth. Its closest approach to our planet will be about 1.8 astronomical units, roughly 168 million kilometers away. That's farther than the distance between Earth and the Sunday. This isn't an extinction event, it's a scientific opportunity. But here's what makes 3I Atlas remarkable. Hubble Space Telescope observations have revealed something extraordinary. This interstellar wanderer is already active, developing a coma, a diffuse cloud of gas and dust, at a distance where most comets remain dormant. We're talking about a structure that may span 700,000 kilometers across, roughly half the diameter of our Sun itself. Think about that for a moment. An object from another star system, carrying chemistry and ices formed in an alien stellar nursery, is creating a bubble of activity so massive it could swallow several Earths without touching the sides. and it's doing this while still millions of kilometers from the sun's warming embrace. Now, I want to be crystal clear about something before we go any further. Mainstream seismology has found no demonstrated causal link between solar storms and earthquakes. The United States Geological Survey, the world's premier earthquake monitoring organization, maintains that tectonic forces drive seismic activity, not space weather. We'll explore the alternative hypotheses as we progress, but we'll label them clearly as speculation, not established fact. That said, the timing island. Curious. The September 14th geomagnetic storm was driven by a recurring trans-equatorial coronal hole, a persistent gap in the sun's magnetic field that had been pumping high-speed solar wind toward Earth for days. This same coronal hole, designated CH1316 by solar physicists, created the conditions for multiple geomagnetic disturbances throughout September. High-speed solar wind streams from coronal holes are different from the dramatic explosions we typically associate with space weather. Instead of a sudden punch, they deliver a sustained pressure that can last for days. The solar wind density drops dramatically, sometimes below 1 particle per cubic centimeter, while velocity increases to nearly double the normal 400 kilometers per second baseline. For those following along at home, you can track these conditions in real time. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center provides continuous updates on the KP index, a measure of geomagnetic disturbance that scales from 0 to 9. Anything above a 4 starts affecting technology. A 6 or 7 can disrupt power grids and GPS systems. The United States Geological Survey maintains equally transparent databases of seismic activity. Every earthquake above magnitude 2.5 is catalogued, analyzed, and made publicly available within minutes of detection. When headlines get noisy, and trust me they will, these are your sources of ground truth. But let's return to our cosmic visitor. 3I Atlas isn't traveling alone through this increasingly active heliosphere. October 2025 promises to be one of the most crowded months for comet watchers in recent memory. Comet C/2025 R2 Swan will make its closest approach to Earth around October 19th through 21st, passing within just 0.26 astronomical units, close enough to develop a tail visible to binoculars. Meanwhile, C/2025, a 6 Lemon, is brightening rapidly, with forecasts suggesting it could reach 4th magnitude by late October. That's bright enough to spot with the naked eye under dark skies, assuming you know where to look. Multiple travelers, an active Sunday, and Earth responding with some of its most powerful seismic releases in over a decade. Coincidence? Perhaps. But as we'll explore in the coming segments, some researchers have proposed mechanisms that could link these phenomena in ways that challenge our understanding of how the solar system operates as an interconnected system. Here's what we know for certain. The sun's magnetic field extends far beyond the visible solar disk, creating a heliosphere that encompasses all the planets and reaches into interstellar space. When objects like 3I Atlas enter this domain, they become part of an electrical circuit spanning billions of cubic kilometers. Their massive comas can interact with the solar wind, the interplanetary magnetic field, and the complex current systems that flow throughout our cosmic neighborhood. The question isn't whether these interactions occur. They absolutely do. The question is whether they're powerful enough to influence geological processes on a planet 150 million kilometers away. Whether the delicate balance of stresses along fault lines could be nudged by changes in the electromagnetic environment that surrounds us all. As we venture deeper into this investigation, we'll examine 3 distinct categories of evidence. First, the verified data, space weather measurements, seismic recordings, and observational astronomy that no one disputes. Second, the contested claims, hypotheses about connections between solar activity and earthquakes that remain hotly debated within the scientific community. And third, the frankly speculative scenarios, the what-if questions that push the boundaries of conventional thinking. Our journey begins with a closer look at the Kamchatka Peninsula, where tectonic forces have created one of Earth's most seismically active regions. But as we'll discover, even the most straightforward geological explanation raises questions about timing, clustering, and the mysterious rhythms that seem to govern when the planet decides to release its stored energy. What happens when an interstellar visitor carrying a plasma cloud half the size of the Sun encounters a star system in the midst of magnetic upheaval? We're about to find out. Part 2. The Kamchatka Cluster. Unprecedented seismic release. Let me paint you a picture of what happened on July 29, 2025. At 14 hours, 55 minutes, and 10 seconds, Coordinated Universal Time, the seafloor off Russia's Kamchatka Peninsula suddenly shifted. In less than 3 minutes, a fault zone that had been locked in place for decades released energy equivalent to 32 billion tons of TNT. The magnitude 8.8 earthquake that followed was so powerful it literally changed the length of Earth's day by microseconds. Within minutes, tsunami warning systems across the Pacific Ocean sprang into action. The Deep Ocean Assessment and Reporting of Tsunamis Network, DART for short, detected waves racing across the Pacific at speeds approaching 800 kilometers per hour. Satellite altimeters from NASA's JASON series confirmed wave heights exceeding 3 meters in the deep ocean, carrying enough energy to level coastal cities thousands of kilometers away. But here's what makes this event extraordinary in the annals of seismology. It wasn't a surprise. Well, not exactly. The Kamchatka Peninsula sits atop one of the world's most active subduction zones, where the Pacific Plate dives beneath the Okhotsk Plate at a rate of about 8 centimeters per year. This ongoing collision has been building stress for centuries, creating the perfect conditions for what seismologists call a megathrust earthquake. The subduction geometry here is textbook, perfect for generating massive seismic events. The descending Pacific Plate creates a gently dipping fault plane that can rupture across hundreds of kilometers simultaneously. When it finally gives way, the overlying plate snaps back like a compressed spring, displacing enormous volumes of seawater in the process. What wasn't expected was the unprecedented clustering of large events that followed. By mid-September, the region had experienced more than 40 aftershocks above magnitude 6, including several that would qualify as major earthquakes in their own right. The September 18th magnitude 7.8 event was just the latest in a sequence that has kept seismologists around the world glued to their monitoring stations. To understand why this clustering matters, you need to appreciate how stress transfers work along fault systems. When a major earthquake occurs, it doesn't just release energy, it redistributes it. Areas that were previously stable suddenly find themselves under increased stress, while others experience what seismologists call stress shadows, where earthquake probability temporarily decreases. The challenge with megathrust events like the July 29th earthquake is that they can trigger cascading failures across vast areas. The initial rupture zone extended nearly 600 kilometers along the plate boundary, but the stress changes it created reached much further. Coulomb stress modeling by the United States Geological Survey suggests that dozens of nearby fault segments experienced increased failure probability following the main shock. This is where traditional seismology and alternative hypotheses begin to diverge. The mainstream explanation for the September 18th event is straightforward. It's a large aftershock, triggered by stress changes from the July earthquake. The magnitude 7.8 classification confirms this interpretation. It's exactly the kind of follow-up event you'd expect in a sequence of this magnitude. But timing is everything in science, and the timing here raises eyebrows. The September 18th earthquake occurred just 3 days after that G3 geomagnetic storm swept through Earth's magnetosphere. Could this be mere coincidence? Or is there a deeper connection between the electrical environment of our planet and the mechanical stresses that drive earthquakes? Before we explore that possibility, let's examine what actually happened during those critical September days. The geomagnetic storm began on September 14th, when a high-speed stream from a coronal hole collided with Earth's magnetosphere. Unlike the sudden impact of a coronal mass ejection, this was a sustained pressure that built gradually over 48 hours. Ground-based magnetometers recorded fluctuations in the magnetic field that reached G3 levels, strong enough to trigger widespread auroral displays and cause minor disruptions to radio communications. More subtly, the storm induced telluric currents in Earth's crust, electrical flows that follow geological structures and can reach surprising intensities along fault zones. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center documented the event in detail. Solar wind speeds peaked at nearly 700 kilometers per second, while particle density dropped to less than 1 proton per cubic centimeter. These conditions create what some researchers call a solar wind vacuum, a low-pressure environment that, according to alternative theories, could influence tectonic processes through electromagnetic coupling. Now, here's where we need to tread carefully. The idea that space weather could trigger earthquakes remains highly controversial within the seismological community. A comprehensive review published in the Journal of Geophysical Research found no statistically significant correlation between geomagnetic storms and earthquake occurrence when proper statistical controls are applied. However, a small number of studies have reported weak correlations under specific conditions. Some researchers point to changes in atmospheric pressure, ionospheric disturbances, or induced currents as potential triggering mechanisms for earthquakes that are already close to failure. The key phrase here is close to failure. No one suggests that space weather could generate earthquakes in stable crustal regions. The Kamchatka Peninsula was anything but stable in September 2025. The region was already experiencing elevated seismic activity following the July megaquake. Aftershock sequences typically follow well-established statistical patterns, with the frequency of events declining according to power laws that have been verified across thousands of earthquake sequences. What makes the September 18th event noteworthy isn't that it occurred. Large aftershocks are expected after magnitude 8.8 events, but rather its precise timing relative to the geomagnetic storm. Statistical analysis would be needed to determine whether this timing falls within expected coincidence ranges or represents something more significant. The physics of potential earthquake triggering by space weather involves several proposed mechanisms. Geomagnetic storms can induce electric currents in conductive geological structures, potentially altering pore fluid pressure along fault planes. Changes in atmospheric pressure associated with ionospheric heating could theoretically influence crustal stress fields. Some researchers even suggest that electromagnetic effects could alter the behavior of fluids within fault zones. But here's the crucial point. Even if these mechanisms exist, they would only affect faults that are already loaded and ready to fail. Space weather cannot create earthquakes out of nothing. It could, at most, advance the timing of events that would occur anyway. The tsunami science emerging from these events deserves special attention. The July 29th earthquake became a real-world test case for next-generation warning systems. NASA's Guardian system, which uses GPS technology to detect ground motion in real time, provided crucial data within minutes of the initial rupture. Combined with the traditional seismic networks and dart buoys, these systems painted an unprecedented picture of how energy propagates through both the solid Earth and the overlying ocean. The waves generated by the July event crossed the Pacific in less than 10 hours, providing a sobering reminder of how quickly tsunamis can travel across oceanic basins. Coastal communities from Alaska to Chile received advance warning, a testament to the international cooperation that has developed in tsunami science since the devastating Indian Ocean event of 2004. As we look toward the remainder of 2025, seismologists continue monitoring the Kamchatka region with intense interest. Statistical models suggest that additional large aftershocks remain possible, with probabilities that will decline slowly over the coming months and years. But here's what traditional models don't account for. We're approaching a unique confluence of astronomical events that hasn't occurred in recorded history. An interstellar comet with a coma spanning hundreds of thousands of kilometers is about to encounter a magnetically active sun at the peak of its 11-year cycle. If electromagnetic coupling between space weather and seismic activity is real, and that's a significant if, then the next few weeks could provide the most compelling test case we've ever had. The question isn't whether correlation equals causation, but whether the correlation is strong enough to warrant serious scientific investigation. The Earth beneath Kamchatka remains restless, its fault zones still adjusting to the massive stress changes of July 29th. Above, the space weather environment grows increasingly turbulent as solar cycle 25 approaches its peak, and somewhere in the darkness between planets, 3I Atlas continues its ancient journey toward a date with our star. What happens when these three domains, geological, solar, and interstellar, converge in the same narrow window of time? The Kamchatka Peninsula may be about to provide the answer, whether we're ready for it or not. Part 3. The Earthquake Generator. There's something peculiar happening in the space around our planet that most people never think about. Right now, as you listen to these words, Earth is surrounded by an invisible river of charged particles flowing from the Sun at speeds that would cross the continental United States in less than 20 seconds. We call it the solar wind, and it's been streaming past our planet for billions of years. But this river isn't constant. Sometimes it races, sometimes it crawls, and sometimes, just sometimes, it creates conditions so unusual that a small group of researchers believes they could literally shake the ground beneath our feet. To understand this phenomenon, we need to talk about coronal holes. Picture the Sun's surface not as a uniform ball of fire, but as a complex magnetic landscape with open and closed field lines. Most of the time, magnetic field lines emerge from the Sun and loop back into its surface, trapping hot plasma in elegant arcs that we see as solar prominences and active regions. But coronal holes are different. Here, the magnetic field lines shoot straight out into space, creating what amounts to a magnetic highway for solar material to escape. The result is a high-speed stream of particles traveling at velocities that can exceed 700 kilometers per second, nearly twice the normal solar wind speed. Here's where it gets interesting for earthquake researchers. When these high-speed streams sweep past Earth, they create what some scientists call a solar wind vacuum. The particle density drops dramatically, sometimes falling below 1 proton per cubic centimeter. To put that in perspective, the air you're breathing contains about 25 billion molecules per cubic centimeter. The solar wind vacuum is emptier than the most perfect vacuum we can create in laboratories. According to a controversial hypothesis that's been circulating in alternative research circles, these vacuum conditions might do something extraordinary. They might pull large earthquakes out of the Earth. The theory goes like this. Earth's crust is under constant stress from tectonic forces, with energy building up along fault lines until they finally snap. But what if external electromagnetic fields could influence when that snapping occurs? What if the electrical environment around our planet, modulated by solar wind conditions, could provide the tiny nudge needed to trigger earthquakes that are already loaded and ready to fail? The mechanism proposed involves a cascade of electromagnetic effects. High-speed solar wind streams create intense geomagnetic disturbances as they compress and stretch Earth's magnetosphere. These disturbances, in turn, induce powerful electric currents in the planet's conducting layers, the ionosphere above and the conductive mantle below. These induced currents, called telluric currents, flow through the Earth's crust following paths of least electrical resistance. They're well-documented phenomena that utility companies monitor carefully because they can damage power transformers and corrode pipelines. But could they also influence fault mechanics? The idea isn't completely far-fetched. Earthquake triggering is an active area of mainstream seismological research. Scientists know that tiny stress changes from tidal forces, atmospheric pressure variations, or even groundwater extraction can advance or delay earthquake timing along faults that are close to failure. The question is whether electromagnetic effects are strong enough to matter. In September 2025, we had what amounted to a natural experiment. A persistent coronal hole, designated CH1316, had been directing high-speed solar wind toward Earth for several days. Solar wind monitoring stations recorded the telltale signature: elevated velocity, reduced density, and the kind of sustained conditions that create prolonged geomagnetic disturbances. The G3 geomagnetic storm that resulted wasn't the most powerful on record, but it was notable for its duration and the specific electromagnetic conditions it created. Ground-based magnetometers detected fluctuations that persisted for more than 48 hours, while ionospheric monitoring stations recorded disturbances that rippled around the globe. 3 days later, the Kamchatka Peninsula shook with that magnitude 7.8 earthquake. Now, correlation doesn't prove causation, and any scientist worth their credentials will remind you of that fundamental principle. The earthquake occurred in a region that was already experiencing intense aftershock activity following July's magnitude 8.8 event. From a purely statistical standpoint, large aftershocks were not just possible but expected. But the timing pattern is what catches the attention of researchers who study these potential connections. According to their analyses, major earthquakes show a tendency to cluster during periods of low solar wind density, those vacuum conditions created by coronal hole streams. The proposed mechanism involves several steps. First, the solar wind vacuum reduces external pressure on Earth's magnetosphere, allowing it to expand. This expansion changes the geometry of electric current systems that flow through the Puseret magnetosphere-ionosphere coupling region. These current changes, in turn, modify the strength and distribution of telluric currents flowing through the Earth's crust. In regions where fault systems intersect conductive geological structures, these current changes could theoretically alter pore fluid pressure, modify the electrical properties of fault-zone materials, or create stress concentrations that weren't there before. The effects would be tiny on an absolute scale, but earthquakes are sensitive to small stress changes when faults are already critically loaded. The research supporting these ideas comes from statistical analyses of earthquake catalogues compared to space weather databases. Some studies report correlations between geomagnetic storm strength and earthquake occurrence, while others find connections to specific solar wind parameters like velocity and density. However, mainstream seismology remains deeply skeptical. The United States Geological Survey, which maintains the world's most comprehensive earthquake database, states clearly that no causal relationship has been established between space weather and seismic activity. Their position, supported by multiple independent analyses, is that the correlations reported in some studies don't hold up when proper statistical controls are applied. The challenge in this field is separating genuine signals from statistical artifacts. Earthquake catalogues contain thousands of events, while space weather databases record continuous variations in dozens of parameters. With so many opportunities for comparison, finding apparent correlations is almost inevitable, even if no real relationship exists. Critics point out several problems with space weather earthquake studies. Selection bias can influence which events and time periods researchers choose to analyze. Multiple comparison effects mean that testing dozens of potential correlations increases the chances of finding spurious relationships. And the physical mechanisms proposed often lack quantitative support from laboratory experiments or theoretical calculations. But proponents argue that the sheer persistence of reported correlations across different datasets, regions, and analysis methods suggests something real might be happening. They point to documented cases where electromagnetic fields have influenced rock mechanics in laboratory settings, and to the growing recognition that Earth's electrical environment is more complex and dynamic than previously understood. The solar wind vacuum hypothesis represents one attempt to provide a physical framework for these observations. By focusing on specific conditions, low-density, high-velocity solar wind streams from persistent coronal holes, it offers testable predictions about when space weather effects might be strongest. As we move through the peak of solar cycle 25, opportunities to test these ideas are multiplying. Coronal holes are more numerous and persistent during solar maximum, creating frequent high-speed stream encounters. At the same time, geomagnetic monitoring has never been more comprehensive, providing detailed measurements of the electromagnetic environment during seismic events. The September 2025 sequence offers one data point in this ongoing investigation. A prolonged coronal hole stream created textbook vacuum conditions, followed within days by a major earthquake in a seismically loaded region. Whether this represents causation, correlation, or simple coincidence remains hotly debated. But here's what makes the next few months particularly intriguing. We're not just dealing with normal solar activity. An interstellar visitor carrying a massive plasma coma is approaching its closest encounter with our star. If electromagnetic coupling between space and Earth is real, 3I Atlas might be about to provide the most dramatic test case in recorded history. The solar wind vacuum isn't just a curiosity for space physicists anymore. It's become a potential window into how our planet responds to the electrical rhythms of the solar system, and as October 2025 approaches, that window is about to get much larger. Whether you believe in earthquake triggering by space weather or not, one thing is certain: the next few weeks will provide plenty of data to analyze. The question is whether that data will support the vacuum hypothesis or finally put it to rest. Either way, the Earth beneath our feet and the plasma flowing past our planet are about to engage in a cosmic conversation that could reshape our understanding of how the solar system really works. Part 4: Planetary Alignment and the G3 Storm. Sometimes the universe has a sense of timing that would make a Hollywood screenwriter jealous. On September 13th, 2025, Mercury reached superior conjunction, the point where it sits directly behind the Sun as viewed from Earth, creating a perfect straight line through space. Less than 24 hours later, a G3 geomagnetic storm crashed into our planet's magnetosphere with enough force to paint the sky green as far south as Kansas. Coincidence? Mainstream heliophysics says absolutely. The storm was clearly driven by a high-speed solar wind stream from a coronal hole that had been tracked for days. Mercury's position, sitting 96 million kilometers away on the far side of the Sun, couldn't possibly influence conditions in the solar wind near Earth. But here's where things get interesting, for those who think outside the conventional box. Some researchers propose that planetary alignments might do something subtle yet significant to the electrical environment of the solar system. Not through gravitational effects, those are far too weak, but through the complex web of electromagnetic interactions that connect all objects within the heliosphere. To understand this possibility, we need to think of the solar system not as a collection of isolated worlds, orbiting through empty space, but as a vast electrical circuit. The Sun sits at the center, pumping out charged particles that create currents flowing throughout the heliosphere. Planets, with their magnetic fields and ionospheres, act like electrical components in this circuit: resistors, capacitors, and inductors, operating on a scale that dwarfs any human technology. When planets align, according to this electrical model, they might change the overall impedance of the heliospheric circuit. Think of it like adding or removing components in an electronic device. The current flow patterns shift, and the system responds in ways that can be difficult to predict. The September 13th Mercury conjunction was particularly notable because it occurred during a period of enhanced solar activity. The Sun was approaching the peak of solar cycle 25, with increased sunspot numbers and more frequent eruptions. Coronal hole CH 1316 had been pumping high-speed solar wind toward Earth for several days, creating the raw material for geomagnetic disturbances. But the storm that arrived on September 14th was stronger than many forecasters had predicted. Initial estimates suggested a G2 moderate storm, but ground-based magnetometers recorded disturbances that reached G3 strong levels. The difference might seem small, but in space weather terms, it represents a significant jump in electromagnetic energy. G3 storms are the point where space weather starts affecting everyday technology in noticeable ways. Aurora displays become visible much further from the poles. Observers reported sightings as far south as Colorado and Illinois. Radio communications experience blackouts, especially at high-frequency ranges used by aviation and maritime industries. GPS accuracy degrades as ionospheric disturbances interfere with satellite signals. More importantly for our investigation, G3 storms induce substantial geomagnetic currents in the Earth's crust. These telluric currents flow through conductive geological structures, following paths determined by underground water, mineralization, and rock types. The currents themselves are well documented. Utility companies have been monitoring them for decades because they can damage transformers and cause cascading power failures. The question is whether these currents are strong enough to influence earthquake processes. Power grid engineers worry about geomagnetically induced currents, reaching hundreds of amperes in transmission lines. But some alternative researchers claim that millions of amperes might flow through deep crustal structures during major geomagnetic storms. The physics of how such currents might trigger earthquakes remains speculative, but several mechanisms have been proposed. Electric currents flowing through fault zones could alter pore fluid pressure by changing the electrochemical properties of groundwater. They might modify the electrical breakdown characteristics of fault materials, making slip more likely under existing stress conditions. Or they could create localized heating that changes rock strength along critical sections of fault planes. Mainstream geophysics finds these mechanisms unconvincing, primarily because the energy involved seems far too small to overcome the mechanical forces that control earthquake occurrence. A typical magnitude 7 earthquake releases energy equivalent to 32 nuclear weapons, while the electromagnetic energy from even severe geomagnetic storms amounts to tiny fractions of that total. But earthquake triggering doesn't require matching the total energy of seismic events. Small stress changes, measured in kilopascals rather than megapascals, can advance earthquake timing when faults are already loaded close to failure. Tidal forces from the moon, for example, can trigger earthquakes, even though their mechanical effects are minuscule compared to tectonic stresses. The key question is whether electromagnetic effects from geomagnetic storms reach stress magnitudes comparable to tidal triggering. Laboratory experiments suggest that electric currents can influence rock fracture processes, but scaling these results to natural fault systems remains challenging. What makes the September 14th storm particularly intriguing is its timing relative to both the Mercury conjunction and the subsequent Kamchatka earthquake. If planetary positions can modulate heliospheric electrical conditions, then alignment events might represent periods of enhanced electromagnetic coupling between space weather and terrestrial processes. The mechanism would work something like this. Planetary alignments alter the large-scale structure of the heliospheric current sheet, the vast spiral of electric current that extends from the Sun's equator throughout the solar system. These changes propagate outward at the speed of light, reaching Earth within 8 minutes of their generation at the Sun's surface. When the modified current sheet encounters Earth's magnetosphere during a geomagnetic storm, the interaction might be amplified compared to normal conditions. The planet's magnetic field channels the enhanced currents into the polar regions, where they connect to the global circuit of telluric currents flowing through the solid Earth. In tectonically active regions like the Kamchatka Peninsula, these currents could theoretically provide the additional stress needed to trigger earthquakes on faults that are already close to failure. The effect would be subtle, perhaps advancing earthquake timing by hours or days rather than creating entirely new events. Testing this hypothesis requires careful statistical analysis of earthquake catalogues compared to both geomagnetic storm records and planetary position databases. Some preliminary studies report weak correlations, but the scientific community remains divided on their significance. The September 2025 sequence provides one data point in this ongoing investigation. Mercury's superior conjunction preceded the G3 storm by less than 24 hours. The storm itself lasted for more than 2 days, creating sustained electromagnetic disturbances. 3 days after the storm began, the Kamchatka Peninsula experienced its magnitude 7.8 earthquake. Whether these events are connected by anything more than chance remains an open question. The time intervals involved, hours between conjunction and storm, days between storm and earthquake, are consistent with proposed electromagnetic triggering mechanisms. But they're also consistent with simple coincidence. As we move deeper into solar cycle 25's maximum phase, opportunities to test these ideas will multiply. Coronal holes become more numerous during solar maximum, creating frequent high-speed stream encounters. Planetary alignments occur regularly throughout the year, providing multiple opportunities to compare electromagnetic conditions. The real test may come in late October, when 3I Atlas reaches perihelion while several other astronomical events unfold simultaneously. If electromagnetic coupling between space weather and earthquakes is real, this period could provide the most compelling evidence yet discovered. But that's assuming the effects remain subtle and localized. What if they're not? What if the electromagnetic environment during the October alignment period proves strong enough to influence seismic activity across multiple regions simultaneously? We're about to enter uncharted territory in the relationship between space weather and terrestrial processes. The Sun is more active than it's been in years, multiple comets are converging on the inner solar system, and planetary positions are creating conditions that haven't occurred in recorded history. The September events may have been just the opening act in a much larger cosmic drama. Whether that drama unfolds as a scientific curiosity or something more consequential depends on questions we're only beginning to learn how to ask. Part 5. the antipodal threat. There's an elegant symmetry to our planet that most people never consider. Draw a line from any point on Earth's surface straight through the center and out the other side, and you'll find its antipode, the exact opposite location on the globe. For most places, that antipode sits somewhere in the middle of an ocean. But for the seismically active Kamchatka Peninsula, something more intriguing emerges. Its antipode falls remarkably close to the Drake Passage, one of the most tectonically active regions in the Southern Ocean. This geographical curiosity has caught the attention of researchers who study what they call energy balance in global seismic systems. Their hypothesis is provocative and largely unproven. When massive earthquakes occur, they create stress imbalances that must eventually be resolved, and sometimes that resolution occurs halfway around the world. The concept draws from both established physics and speculative geodynamics. We know that large earthquakes generate seismic waves that propagate completely around the Earth. These waves, particularly the long-period surface waves that can circle the globe multiple times, carry information about the earthquake's magnitude, depth, and rupture characteristics to every point on the planet's surface. But what if they carry something more? What if they transport actual stress changes that accumulate over time, creating conditions for future earthquakes in locations that seem completely unrelated to the original event? The July 29th magnitude 8.8 Kamchatka earthquake certainly generated enough energy to test this hypothesis. Its seismic waves were recorded by monitoring stations on every continent, with some instruments detecting motion more than 12 hours after the initial rupture. The waves circled Earth multiple times before finally dissipating into the background. Noise of continuous seismic motion. In the process, they passed through every major fault system on the planet, including the complex network of transform faults, spreading ridges, and subduction zones that surround the Southern Ocean. The Drake Passage region is particularly sensitive because it sits at the intersection of three major tectonic plates, the Antarctic, South American, and Scotia plates, creating a zone where stress can accumulate and release in unpredictable patterns. The antipodal hypothesis suggests that energy from the Kamchatka earthquake might have been deposited in these Southern Ocean structures, creating conditions for a delayed response earthquake. The mechanism isn't clearly defined. It could involve direct stress transfer through deep Earth layers, resonance effects that amplify local stress concentrations, or more exotic processes involving the planet's magnetic field and electrical conductivity structure. What makes this idea particularly compelling to its proponents is the timing window they've identified. Based on historical analysis of antipodal earthquake pairs, they suggest that delayed responses typically occur within 2 to 6 months of the original event. The July 29th Kamchatka earthquake puts us squarely within that window as we move through October and November 2025. But here's where we need to apply some healthy skepticism. Mainstream seismology doesn't recognize antipodal earthquake triggering as a validated phenomenon. The United States Geological Survey and other authoritative agencies base their earthquake forecasts on local geological conditions, stress accumulation rates, and statistical models derived from regional seismic histories. Global stress transfer is real. That's well-established science. Large earthquakes do change stress conditions across thousands of kilometers, and these changes can advance or delay earthquake timing along connected fault systems. But the effects typically diminish rapidly with distance, following well-understood mathematical relationships based on fault geometry and crustal properties. Antipodal triggering would require energy transmission across 12,700 kilometers of solid Earth, the maximum possible distance between any 2 points on the planet's surface. While seismic waves certainly travel these distances, the idea that they could create stress concentrations sufficient to trigger major earthquakes remains highly speculative. The challenge lies in the energy budget calculations. A magnitude 8.8 earthquake releases approximately 10 to the power of 17 joules of energy, equivalent to about 32 megatons of TNT. But most of that energy is dissipated as heat and seismic wave radiation within the first few hundred kilometers of the rupture zone. The fraction that reaches antipodal distances is tiny compared to the local tectonic forces that control earthquake occurrence. However, proponents of antipodal triggering point to several historical examples that seem to support their hypothesis. The December 2004 Sumatra earthquake was followed 4 months later by a magnitude 8.6 event on the same fault system. The March 2011 Tohoku earthquake preceded unusual seismic activity in several antipodal regions, though no single large event clearly matched the predicted pattern. More intriguingly, some researchers have identified apparent correlations between earthquake sequences in the Pacific Ring of Fire and contemporaneous activity along the mid-Atlantic ridge system. These correlations, if real, would suggest global-scale stress transfer mechanisms that aren't fully understood by conventional seismology. The Drake Passage region presents a particularly interesting test case because of its unique geological setting. The passage represents the youngest oceanic gateway on Earth, having opened only 34 million years ago when South America and Antarctica finally separated. This relatively recent geological history means that the fault systems here are still adjusting to their new configuration. The region experiences regular seismic activity along the South American Antarctic ridge system, with typical events ranging from magnitude 5 to 7. But the complex interaction between spreading ridges, transform faults, and the nearby South Sandwich subduction zone creates conditions where larger events remain possible. If antipodal energy transfer is real, we might expect to see several signatures in the Drake Passage region during the coming months. Increased seismic activity across multiple fault systems would suggest broad stress changes rather than localized effects. Changes in earthquake focal mechanisms, the orientation of rupture planes, might indicate altered stress fields, and the timing of any major events would need to fall within the predicted window for antipodal responses. The electromagnetic component of this hypothesis adds another layer of complexity. Some researchers propose that antipodal earthquake triggering isn't purely mechanical, but involves electrical effects propagating through Earth's conductive layers. This idea connects the seismic energy balance concept to the broader electromagnetic theories we've been exploring. According to this electromagnetic variant, the Kamchatka earthquake created not just mechanical stress changes, but also electrical disturbances that propagated through the planet's conductive mantle and core. These disturbances could theoretically influence seismic processes in antipodal regions through the same mechanisms proposed for space weather triggering: changes in pore fluid pressure, altered electrical breakdown characteristics of fault materials, or localized heating effects. The timing of such electromagnetic propagation would be much faster than mechanical stress transfer, potentially explaining some of the shorter-term correlations observed in historical earthquake catalogues. Electrical signals travel at significant fractions of light speed through conductive materials, meaning antipodal effects could appear within hours or days rather than months. Testing these ideas requires sophisticated analysis of global seismic databases, combined with electromagnetic monitoring data. Some research groups have reported promising preliminary results, but the scientific mainstream remains skeptical. The signal-to-noise ratio in global earthquake catalogues is challenging, and the multiple variables involved make it difficult to establish clear causal relationships. What makes the current period particularly intriguing is the convergence of multiple potential triggering mechanisms. We have the ongoing aftershock sequence from the July Kamchatka earthquake, elevated solar activity from solar cycle 25, and the approaching perihelion of 3I Atlas with its massive electromagnetic coma. If antipodal triggering exists, this combination of factors might create the strongest test case in recorded history. The mechanical stress transfer from Kamchatka, electromagnetic effects from space weather, and potential interactions with the interstellar visitor's plasma environment could theoretically combine to influence seismic processes across multiple regions simultaneously. The Drake Passage represents just one potential target in this scenario. Other antipodal regions to recent large earthquakes include areas of the Atlantic and Indian Ocean basins, where transformed fault systems could respond to global stress changes. The key will be watching for patterns of activity that exceed normal background rates while falling within predicted timing windows. As we move through October and November 2025, seismologists around the world will be monitoring these regions with particular attention, not because they necessarily believe in antipodal triggering, but because the convergence of so many unusual factors creates an unprecedented natural experiment. Whether that experiment validates alternative earthquake theories or reinforces conventional understanding remains to be seen. But the data collected during this period will undoubtedly contribute to our evolving knowledge of how Earth responds to both internal and external energy sources. The planet beneath our feet is a complex, interconnected system where stress changes in one location can influence processes thousands of kilometers away. As we're about to discover, it may also be sensitive to influences from much further afield, including visitors from the space between stars. The energy balance hypothesis suggests that Earth maintains a kind of seismic equilibrium, where major disruptions in one region eventually trigger compensating responses elsewhere. If that's true, then the July Kamchatka earthquake created an imbalance that still demands resolution. The question isn't whether that resolution will come, it's where, when, and whether we'll be prepared to recognize it when it does. Part 6. The anomalous interstellar object. In the 1970s, astronomer Carl Sagan famously observed that we live in a universe where extraordinary claims require extraordinary evidence. By that standard, 3I Atlas presents us with quite a puzzle. This isn't just another comet wandering through our solar system, it's a messenger from deep space, carrying chemistry and materials forged in the stellar nurseries of distant suns. The formal designation tells the story, 3I Atlas, where the I stands for interstellar, and the number 3 indicates that this is only the third confirmed visitor from beyond our solar system. The first, 1I/Oumuamua, baffled astronomers when it arrived in 2017 with its cigar-shaped profile and mysterious acceleration. The second, 2I/Borisov, proved more conventional, clearly a comet, behaving much as expected when it passed through in 2019. 3I Atlas falls somewhere between familiar and extraordinary, and that's what makes it so intriguing. The object was first detected by the Asteroid Terrestrial Impact Last Alert System telescope network in 2025, appearing as little more than a fuzzy dot moving against the background stars. But orbital calculations quickly revealed its true nature. This was no asteroid or conventional comet. The trajectory was clearly hyperbolic, indicating speeds and angles that could only result from an origin far beyond our Sun's gravitational influence. Initial observations suggested something unusual about 3I Atlas from the very beginning. Most comets remain dormant until they approach within 2 or 3 astronomical units of the Sun, roughly the distance of the asteroid belt. But this interstellar visitor was already showing signs of activity at distances where solar heating should barely register. The Hubble Space Telescope's first detailed images confirmed what ground-based observers had suspected. 3I Atlas was developing a coma, that characteristic cloud of gas and dust that gives comets their distinctive appearance. But this coma was forming under conditions where conventional cometary physics suggested it shouldn't exist. More puzzling still were the morphological details that emerged from extended observations. Unlike typical comets, which develop relatively symmetrical comas centered on their nucleus, 3I Atlas displayed what astronomers call forward brightening or leading coma structures. The brightest regions of its envelope appeared ahead of the nucleus in its orbital motion, suggesting complex outgassing patterns driven by rotation and surface properties unlike anything in our local comet population. The spectroscopic analysis revealed another surprise. While most comets in our solar system are dominated by water ice with traces of carbon monoxide and carbon dioxide, 3I Atlas showed an unusually rich carbon dioxide signature. This composition makes sense for an object formed in the past, cold reaches between stars, where carbon dioxide would remain frozen, while water ice might be depleted by various processes. But it's the scale of 3I Atlas that truly sets it apart. Estimates of its nucleus size, derived from Hubble observations and thermal modelling, suggest a relatively modest object, perhaps 3 to 6 kilometers across. That's substantial but not unprecedented in the comet world. What's extraordinary is the size of the coma it's producing. Current measurements indicate that the gaseous envelope surrounding 3I Atlas extends to at least 348,000 kilometers from its center, creating a roughly spherical cloud with a diameter of approximately 700,000 kilometers. To put that in perspective, You could fit nearly 50 Earths side by side across the width of this interstellar visitor's coma. That makes 3I Atlas comparable in extent to some of the largest structures in our solar system. The Sun itself has a diameter of about 1.4 million kilometers, meaning this comet's coma spans roughly half the width of our star. It's a ghostly, diffuse bubble of gas and dust drifting through space on a scale that challenges our intuitions about what comets should look like. The physics behind such an enormous coma from a relatively small nucleus involves several factors unique to interstellar objects. Unlike solar system comets, which have been processed by billions of years of solar radiation and gravitational perturbations, 3I Atlas represents pristine material from its original stellar environment. The ice mixture it carries may be more volatile than anything we're familiar with, leading to enhanced outgassing even at large solar distances. The object's rotation also plays a crucial role. Preliminary observations suggest a rotation period of several hours, typical for small solar system bodies, but the distribution of surface materials may be highly heterogeneous, with some regions rich in volatile ices while others remain relatively inert. This patchwork composition could explain the asymmetrical coma structure and the unusual forward brightening phenomenon. As 3I Atlas approaches its October 30th perihelion, the coma will almost certainly continue growing. Increased solar heating will vaporize more surface and subsurface ices, potentially expanding the envelope to dimensions that dwarf even its current impressive size. Some models suggest the coma could reach diameters exceeding 1 million kilometers, larger than the Sun itself. But here's what makes this particularly fascinating from a space physics perspective. That enormous coma isn't just a passive cloud of gas and dust. It's an electrically active plasma structure interacting with the solar wind and interplanetary magnetic field in ways we've never had the opportunity to study. When solar wind particles collide with neutral atoms and molecules in the coma, they can strip away electrons, creating ions that respond to electromagnetic forces. These newly created ions get swept up by the solar wind and carried away from the comet, forming the characteristic ion tail that points away from the Sunday. For an object with a coma spanning hundreds of thousands of kilometers, this interaction zone becomes truly massive. 3I Atlas is essentially dragging a spherical net through the solar wind, one that's sensitive to variations in magnetic field strength, particle density, and plasma temperature. It's become an interstellar probe of heliospheric conditions, responding to space weather in ways that could provide unprecedented insights into the electromagnetic environment around our Sunday. The timing of its arrival couldn't be more perfect for scientific study. Solar cycle 25 is approaching maximum activity, with increased solar flares, coronal mass ejections, and high-speed wind streams. The heliosphere is more dynamic and turbulent than it's been in over a decade, providing 3I Atlas with a rich variety of plasma, conditions to sample and respond to. NASA's James Webb Space Telescope has been tracking the object's spectroscopic evolution, while ground-based observatories monitor changes in coma morphology and tail development. The European Space Agency's Solar Orbiter mission is positioned to provide complementary measurements of solar wind conditions as 3I Atlas encounters different regions of heliospheric activity. What we're witnessing is essentially a controlled experiment in plasma physics, on a scale impossible to replicate in any laboratory. An object from another star system is serving as a probe of our local space environment, revealing details about magnetic field structures and particle interactions that would otherwise remain invisible. But 3I Atlas represents more than just a scientific opportunity. It's a reminder that our solar system isn't isolated from the galaxy around it. Objects drift between stars regularly, carrying with them the chemical signatures and physical processes of distant stellar neighborhoods. We're getting a sample of alien materials and alien physics delivered right to our cosmic doorstep. The question that some researchers are beginning to ask is whether 3I Atlas might be carrying more than just scientific interest. Its enormous electromagnetic footprint and peculiar interaction with solar wind conditions have prompted speculation about whether such objects could influence space weather in measurable ways. As we'll explore next, that speculation leads to some remarkably exotic possibilities about what interstellar visitors might represent and what they might be capable of accomplishing during their brief passages through our solar system. For now, 3I Atlas continues its ancient journey toward a date with our Sun, growing brighter and more active with each passing day. Whatever secrets it holds about its distant origins, it's about to share them with us in the most dramatic way possible. The universe has sent us a messenger from the space, between stars. The only question is whether we're prepared to understand what it's trying to tell us. Part 7. The Coma, half the diameter of the Sun. Picture, if you will, a soap bubble floating through space, but a soap bubble so enormous that you could fit 25 Earths inside it with room to spare. That's the scale we're dealing with when we talk about the coma of 3I Atlas, a gossamer envelope of gas and dust that has grown to dimensions that challenge our understanding of what comets can become. The latest measurements from infrared space telescopes paint a picture that seems almost impossible. The coma extends at least 348,000 kilometers in radius from the object's nucleus, creating a sphere of activity roughly 700,000 kilometers across. To put that in cosmic context, this interstellar visitor has created a bubble that spans more than half the diameter of our Sunday. That comparison isn't just a neat astronomical fact, it's a window into physics operating on scales we rarely encounter. The Sun is a massive ball of plasma held together by its own gravity, generating temperatures of millions of degrees in its core. 3I Atlas is a tiny chunk of ice and rock, probably no bigger than a small mountain, creating a structure that rivals our star in sheer size through completely different processes. The key to understanding this phenomenon lies in the nature of cometary comas themselves. When we see a comet in the night sky, that glowing head isn't the solid nucleus. It's a cloud of gas and dust particles that have been liberated from the surface by solar heating. As frozen ices sublimate directly from solid to vapor, they carry dust particles along with them, creating an expanding envelope around the nucleus. For most comets in our solar system, this process begins gradually when they venture inside the orbit of Jupiter and roughly 5 astronomical units from the Sunday. The coma typically reaches maximum size around perihelion, the closest approach to the Sun, then slowly dissipates as the object moves back toward the outer solar system. But 3I Atlas is breaking all the conventional rules. It began showing cometary activity while still beyond 3.8 astronomical units from the Sun, at distances where solar heating should barely register. This early onset of activity suggests that the object carries ices that are far more volatile than the water-dominated compositions typical of solar system comets. The spectroscopic signature tells part of the story. Unlike local comets, which are primarily water ice with traces of carbon monoxide and carbon dioxide, 3I Atlas shows a composition dominated by carbon dioxide and other exotic ices. These materials sublimate at much lower temperatures than water, explaining how the object can maintain such an enormous coma while still relatively far from the Sunday. Carbon dioxide ice begins sublimating at around -78 degrees Celsius under Earth atmospheric pressure. In the near vacuum of space, sublimation can occur at even lower temperatures, driven by the faint heat of distant sunlight. This means 3I Atlas has been steadily outgassing for months as it approaches perihelion, building its massive coma particle by particle. But size alone doesn't capture the full strangeness of this structure. The coma isn't a uniform sphere of gas and dust. It's a complex dynamic environment where multiple physical processes operate simultaneously. Solar radiation pressure pushes small dust particles away from the Sun, creating the characteristic dust tail that can stretch millions of kilometers behind a comet. Meanwhile, the solar wind, that stream of charged particles flowing from the Sun at 400 kilometers per second, interacts with the neutral gas in the coma through a process called photoionization. When high-energy photons from the Sun strike neutral atoms and molecules, they can knock electrons free, creating ions that suddenly become responsive to magnetic fields. These newly created ions get swept up by the solar wind and carried away from the comet at tremendous speeds, forming the blue ion tail that always points directly away from the Sun regardless of the comet's motion. For an object with a coma spanning hundreds of thousands of kilometers, this ionization process creates a vast region of active plasma chemistry. Think of 3I Atlas as dragging an enormous net through the solar wind, one that's constantly sampling the electromagnetic environment around our Sunday. Variations in solar wind speed, density, and magnetic field strength all influence how the coma responds. During periods of enhanced solar activity, like the geomagnetic storms we've been experiencing, the interaction becomes even more complex and energetic. The forward brightening phenomenon observed in 3I Atlas adds another layer of complexity to this picture. Most comets develop relatively symmetric comas centered on their nucleus, but this interstellar visitor shows its brightest regions ahead of the nucleus in its orbital direction. This asymmetry suggests that outgassing is concentrated on specific regions of the surface, possibly due to the object's rotation or heterogeneous composition. As 3I Atlas rotates, different surface areas face the Sun, leading to episodic outgassing that creates structures within the coma. These internal features can persist for days or weeks, creating a constantly evolving landscape of gas and dust that responds to both solar heating and the object's own dynamics. The scale of this activity becomes truly impressive when you consider the mass loss rates involved. Current estimates suggest 3I Atlas is losing several kilograms of material per second as it approaches perihelion. That might not sound like much, but sustained over months, it represents thousands of tons of pristine interstellar material being dispersed throughout the inner solar system. This material carries with it the chemical signature of the stellar environment where 3I Atlas formed billions of years ago. Spectroscopic analysis of the coma provides a direct sample of interstellar chemistry, offering insights into the conditions around other stars that we could never obtain through any other means. But the coma represents more than just scientific opportunity. It's also an electromagnetic phenomenon of unprecedented scale. The ionized component of the coma creates a huge volume of space where plasma physics operates under conditions we've never been able to study before. The interaction between this plasma and the local magnetic field environment could theoretically influence space weather conditions throughout the inner solar system. Some researchers have begun to speculate about whether objects like 3I Atlas might act as natural space weather modifiers, their enormous comas serving as plasma reservoirs that could amplify or dampen electromagnetic disturbances. The idea remains highly speculative, but the sheer scale of the interaction region makes it worth considering. As we approach the October 30th perihelion, the coma will almost certainly continue growing. Increased solar heating will vaporize more surface ices, potentially expanding the envelope to dimensions that exceed the Sun's diameter. Some models suggest peak coma sizes could reach 1.2 million kilometers across, creating a structure larger than any permanent feature in our solar system except the Sun itself. The visibility of this enormous structure from Earth remains limited, unfortunately. Despite its impressive size, the coma is extremely diffuse, with particle densities far lower than Earth's atmosphere at high altitude. Most of the mass is concentrated in the dust tail, which may become visible to skilled observers with telescopes as the object rounds the sunday. But the real drama is happening at wavelengths invisible to human eyes. Radio telescopes are detecting emissions from the ionized, the component of the coma, while infrared satellites track the thermal signature of dust particles being heated by sunlight. X-ray observatories monitor high-energy processes in the interaction region between the coma and solar wind. What we're witnessing is a masterclass in plasma physics being taught by a visitor from another star. 3I Atlas has created a natural laboratory for studying electromagnetic interactions on scales impossible to replicate on Earth, revealing details about how matter and energy behave in the space environment around our sunday. The question that's beginning to emerge from all these observations is whether 3I Atlas might be more than just a passive chunk of ice and rock wandering through space. Could an object capable of creating such an enormous electromagnetic signature actually influence the space weather conditions it's sampling? That possibility leads us into territory that's equal parts science and science fiction, where the boundaries between natural phenomena and technological capabilities begin to blur in ways that challenge our assumptions about what's possible in the universe. Part 8. What if 3I Atlas is an alien energy harvester? Let's venture into the realm of pure speculation for a moment, but speculation grounded in physics that might not be as far-fetched as it first appears. What if 3I Atlas isn't simply a chunk of pristine ice and rock from another star system? What if it's something far more extraordinary, a massive energy collection device, engineered by an intelligence we can barely imagine, designed to harvest power from stars as it travels between solar systems. The idea sounds like science fiction, but consider the evidence we've already discussed. A relatively small nucleus, perhaps 3 to 6 kilometers across, generating a coma that spans 700,000 kilometers. That's an efficiency ratio that would make any engineer envious. A structure less than 6 kilometers wide, creating an active zone, more than 100,000 times larger. From an energy collection standpoint, that enormous coma begins to look less like random outgassing and more like a deliberately engineered plasma sail. Imagine a technology that could deploy a gossamer net of conductive materials, one that expands to enormous dimensions while maintaining the ability to channel collected energy back to a central processing core. The physics isn't impossible. We already know that electromagnetic fields can accelerate charged particles to tremendous velocities. That's the principle behind plasma engines and magnetic confinement fusion. What if 3I Atlas represents a scaled-up version of these technologies, one designed to operate in the natural plasma environment around stars? The forward brightening phenomenon we've observed could represent active guidance systems rather than random surface features. If the object were using controlled outgassing to modify its trajectory or optimize its interaction with the solar wind, we might expect to see exactly the kind of asymmetrical activity that has puzzled astronomers. The carbon dioxide-rich composition takes on new significance in this context. Unlike water, which requires significant heating to sublimate, carbon dioxide can transition directly from solid to gas at the low temperatures found in outer space. This makes it an ideal propellant for a system that needs to operate across a wide range of stellar distances. But energy collection would require more than just a large plasma interaction region. It would need some mechanism for channeling the collected energy to useful purposes. Here's where the physics gets interesting. The same processes that create ion tails in comets could theoretically be used to generate electrical currents on an enormous scale. When solar wind particles ionize neutral atoms in the coma, they create charged particles that respond to magnetic fields. In a natural comet, these ions simply get swept away by the solar wind. But what if 3I Atlas contains embedded magnetic field generators that could guide these ions along specific pathways? Such a system could function like a massive magneto-hydrodynamic generator, converting the kinetic energy of solar wind particles into electrical current. The scale would be unprecedented. We're talking about a power collection area measured in millions of square kilometers, operating in an environment where particle velocities routinely exceed 500 kilometers per second. The energy budget becomes impressive when you run the numbers. The solar wind carries approximately 10 to the power of -3 watts per square meter at Earth's distance from the Sunday. For an interaction cross-section, the size of 3I Atlas's coma, that translates to potential power collection in the terawatt range, equivalent to hundreds of large power plants. Of course, conversion efficiency would be crucial. Natural plasma interactions are notoriously inefficient, with most energy dissipated as heat and electromagnetic radiation. But an engineered system might achieve efficiencies that nature cannot, using superconducting materials or exotic magnetic field configurations to maximize energy capture. The question becomes, what would such a system do with terawatts of collected power? One possibility is energy storage, perhaps through the creation of exotic matter states or high-energy particle configurations that could be maintained over interstellar distances. Another is active propulsion, using the collected energy to accelerate reaction mass and modify the object's trajectory through space. From a strategic standpoint, a solar energy harvester makes sense for any civilization attempting to explore or colonize the galaxy. Stars are the most concentrated energy sources available, and a technology that could efficiently tap stellar output would provide enormous advantages for interstellar travel. Such devices could serve multiple functions: energy collection, propulsion, communication, and scientific exploration. They might operate autonomously for millions of years, following predetermined routes between star systems while gathering data and resources for their creators. The von Neumann probe concept, proposed by mathematician John von Neumann in the 1940s, describes self-replicating machines that could spread throughout the galaxy by harvesting materials and energy from stellar systems they encounter. 3. I-Atlas might represent a more subtle version of this concept, not self-replicating, but self-sustaining through stellar energy harvesting. But here's where we need to apply some skeptical thinking. If 3 I-Atlas were artificial, we might expect to see signatures that clearly distinguish it from natural objects. Unusual spectroscopic lines, non-thermal radiation, or trajectory changes that can't be explained by gravitational and outgassing forces. So far, most observations of 3 I-Atlas appear consistent with natural cometary behavior, albeit on an unusual scale. The spectroscopic signature shows the expected atomic and molecular lines from sublimating ices. The trajectory follows a hyperbolic orbit that could result from gravitational ejection from another star system. The non-gravitational acceleration observed in some comets, including one I/Oumuamua, could theoretically result from artificial propulsion systems. But it could also be explained by asymmetrical outgassing or other natural processes that we don't fully understand. The key test would be detecting technology signatures, artificial materials, coherent electromagnetic emissions, or systematic behavioral patterns that suggest deliberate control. Radio telescope searches for signals from 3 I-Atlas have so far found nothing beyond the natural emissions expected from plasma interactions. Still, the absence of obvious artificial signatures doesn't necessarily rule out advanced technology. A sufficiently sophisticated civilization might design their probes to mimic natural phenomena, avoiding detection by less advanced species they encounter during their travels. This mimicry could serve several purposes: scientific, to avoid contaminating observations of natural systems; strategic, to prevent interference with local civilizations; or protective, to avoid revealing the probe's true capabilities to potentially hostile species. From this perspective, 3 I-Atlas's apparent naturalness might actually be evidence of artificial origin. A technology designed to harvest stellar energy while remaining undetectable would need to perfectly mimic the behavior of natural interstellar objects. The timing of its arrival during solar cycle 25 maximum could be coincidental, or it could represent optimal conditions for energy collection. A sophisticated probe might time its perihelion passage to coincide with periods of maximum stellar activity, when solar wind conditions provide the richest energy environment. The electromagnetic effects we've been exploring throughout this investigation take on new significance in this context. If 3 I-Atlas were actively harvesting solar energy, it might generate electromagnetic signatures that could influence space weather conditions throughout the inner solar system. Such influences might be intentional, perhaps designed to test the response characteristics of planetary magnetospheres, or simply unavoidable consequences of large-scale energy collection processes operating in the heliospheric environment. The earthquake correlations we've been examining might represent sensitivity to these electromagnetic signatures rather than responses to natural space weather variations. If 3 I-Atlas were modulating local space weather conditions through its energy harvesting activities, terrestrial systems might respond in ways that appear mysterious when we assume purely natural causes. This speculation leads us to even more exotic possibilities. What if earthquake triggering isn't an accidental, the side effect of alien energy harvesting, but rather a deliberate test of planetary seismic systems? Could 3 I-Atlas be conducting a systematic survey of Earth's geological responses to electromagnetic stimulation? The idea pushes us well beyond conventional scientific thinking into territory that most researchers would dismiss as pure fantasy. But as we'll explore next, the possibility of directed energy effects, whether natural or artificial, raises profound questions about the nature of the phenomena we've been investigating. Whether 3 I-Atlas is a chunk of ancient ice or a masterpiece of alien engineering, its passage through our solar system represents an unprecedented opportunity to observe plasma physics on a scale we've never encountered before. The question is whether we're prepared to recognize what we're seeing, regardless of what it might ultimately prove to be. Part 9. Earthquakes as Directed Energy. Here's where our investigation ventures into territory that would make most seismologists reach for their blood pressure medication. What if the earthquake patterns we've been tracking aren't random geological events responding to natural space weather? What if they represent something far more unsettling? Directed energy effects, systematically probing Earth's crustal response characteristics, with the precision of a controlled experiment. The idea sounds absurd at first glance, but consider the patterns we've already established. High-speed solar wind streams create low-density vacuum conditions that some researchers believe can trigger earthquakes on loaded fault systems. The timing correlations are suggestive, even if the physical mechanisms remain disputed by mainstream science. But what if those vacuum conditions aren't entirely natural? What if an advanced technology could modulate solar wind characteristics, creating precisely the electromagnetic conditions needed to influence seismic activity on a planetary scale? The concept requires thinking about energy and information on scales that challenge human intuition. We're accustomed to earthquakes as chaotic, unpredictable events, driven by the slow accumulation of tectonic stress over decades or centuries. The idea that they could be triggered by external electromagnetic fields seems to violate everything we know about crustal mechanics. Yet the energy budget calculations aren't as impossible as they might first appear. Major earthquakes do release enormous amounts of energy, equivalent to hundreds of nuclear weapons, but that energy was already stored in the system through tectonic loading. Triggering doesn't require matching the total energy output. It merely requires providing the small additional stress needed to initiate failure on faults that are already critically loaded. Laboratory experiments have demonstrated that electromagnetic fields can influence rock fracture processes under controlled conditions. Electric currents flowing through rock samples can alter their mechanical properties, change pore fluid pressure, or create localized heating that affects failure thresholds. The question is whether these laboratory-scale effects could be scaled up to influence natural fault systems. If an advanced technology wanted to study planetary seismic systems, systematic triggering experiments would provide invaluable data. By creating controlled electromagnetic conditions and observing the resulting seismic responses, such a system could map fault-loading states, crustal structure, and stress transfer mechanisms with unprecedented precision. The historical record provides some intriguing data points for this speculation. When 1I/Oumuamua made its closest approach to the Sun in September 2017, Mexico experienced a devastating magnitude 8.2 earthquake just days later. The Tohoku earthquake of March 2011 occurred during a period of elevated solar activity, with several significant geomagnetic storms in the FI, weeks preceding the event. These correlations prove nothing, of course. Earthquakes occur regularly, and space weather events are common during solar maximum periods. Finding apparent connections between astronomical events and seismic activity is almost inevitable when you're looking through decades of data. But the patterns become more interesting when you consider the global distribution of major earthquakes during periods of unusual astronomical activity. The 2004 Sumatra earthquake, the 2010 Chile event, the 2011 Japan disaster, all occurred during solar cycle periods, characterized by enhanced space weather activity. More intriguingly, some of these events showed unusual precursor patterns that suggested external triggering rather than purely tectonic causes. Changes in groundwater levels, electromagnetic anomalies, and atmospheric disturbances that began days or weeks before the main shocks, all phenomena that could theoretically result from systematic electromagnetic probing of crustal systems. If 3I Atlas represents an advanced probe rather than a natural comet, its enormous electromagnetic footprint would provide an ideal platform for conducting such experiments. The object's massive coma creates a plasma interaction region larger than most planets, one that could theoretically channel and focus electromagnetic effects across millions of cubic kilometers of space. The technology required wouldn't necessarily violate known physics. Magnetic field manipulation using superconducting coils could create focusing effects that concentrate electromagnetic energy at specific planetary locations. Plasma injection systems could modulate solar wind characteristics, creating the vacuum conditions that some researchers associate with earthquake triggering. The precision timing we've observed between space weather events and seismic activity could reflect sophisticated understanding of crustal loading cycles and stress accumulation patterns. An advanced monitoring system might track fault conditions continuously, waiting for optimal moments when small electromagnetic perturbations could trigger large responses. Such a system might operate through multiple mechanisms simultaneously. High-frequency electromagnetic pulses could alter the electrical properties of fault-zone materials, Low-frequency magnetic field variations could induce telluric currents that change pore fluid pressure. Plasma injection into the ionosphere could create atmospheric pressure waves that propagate downward to influence crustal stress fields. The targeting wouldn't need to be perfectly precise. Fault systems are complex, interconnected networks where stress changes in one location can trigger cascading failures across hundreds of kilometers. A technology that could create broad regional electromagnetic anomalies might be sufficient to influence seismic activity patterns without requiring pinpoint accuracy. But why would an advanced civilization want to conduct such experiments? The motivations could range from purely scientific curiosity to more practical considerations about planetary habitability and resource distribution. Understanding seismic systems would be crucial for any civilization considering planetary colonization. Earthquake patterns reveal information about crustal structure, resource distribution, and long-term geological stability. A comprehensive seismic survey could identify optimal locations for infrastructure development while avoiding regions prone to catastrophic geological activity. From a more ominous perspective, demonstrated ability to trigger earthquakes would represent an ultimate strategic capability. The capacity to devastate coastal cities or disrupt critical infrastructure through remote electromagnetic manipulation would provide enormous leverage in any interplanetary diplomatic scenario. The ethical implications are staggering. If major earthquakes could be artificially triggered, the humanitarian consequences would be beyond calculation. The 2004 Indian Ocean tsunami killed nearly 250,000 people. The 2011 Tohoku disaster caused multiple nuclear reactor meltdowns. The idea that such events might result from alien experiments is almost too horrifying to contemplate. Yet the possibility forces us to confront uncomfortable questions about the nature of the phenomena we've been observing. The correlations between space weather and seismic activity, the unusual timing patterns, the unprecedented convergence of astronomical events during solar cycle 25, all could be interpreted as evidence of systematic investigation rather than natural coincidence. The challenge lies in distinguishing between directed effects and natural phenomena that we don't fully understand. Advanced plasma physics operating on heliospheric scales might produce effects that appear artificial when observed from our limited perspective. Natural interactions between massive cometary comas and solar wind conditions could create electromagnetic signatures that mimic technological systems. The key test would be detecting patterns that clearly indicate intelligence and purpose rather than natural variability. Systematic targeting of specific fault systems, precise timing that correlates with optimal stress loading conditions, or electromagnetic signatures that show technological rather than natural characteristics. So far, the seismic patterns we've observed remain within the range of natural variability, even if their timing relative to space weather events is suggestive. The Kamchatka Peninsula experienced its major earthquakes in a region that was already seismically loaded following tectonic processes that have been ongoing for millions of years. But the October perihelion passage of 3I Atlas may provide a more definitive test. If the object represents advanced technology rather than a natural comet, its closest approach to the Sun might coincide with enhanced electromagnetic effects that could influence seismic activity in measurable ways. The global seismic monitoring network has never been more comprehensive than it is today. Every earthquake above magnitude 4 is detected within minutes by multiple stations, providing unprecedented resolution of timing, location, and source mechanisms. If directed energy effects exist, the October period should reveal patterns that clearly distinguish them from natural seismic processes. The electromagnetic monitoring capabilities are equally sophisticated. Magnetometer networks span the globe, while satellite systems provide continuous measurements of space weather conditions throughout the heliosphere. Any technological manipulation of electromagnetic fields should leave signatures that can be distinguished from natural solar and geomagnetic variability. The disturbing aspect of this speculation isn't just the possibility that earthquakes might be artificially triggered, but what it would imply about our understanding of the universe around us. The discovery that major geological events could result from alien technology would fundamentally challenge our assumptions about planetary security and our place in the cosmic community. It would suggest that civilizations advanced enough for interstellar travel might view planets like Earth as natural laboratories, suitable for experiments that could cause massive humanitarian disasters for the inhabitants. The ethical frameworks that govern such activities would presumably be as alien as the technology itself. From a more optimistic perspective, systematic seismic monitoring might represent a form of planetary survey, gathering data about crustal structure and geological processes that could prove valuable for future scientific collaboration. The triggering effects, if real, might be unfortunate but unintended consequences of legitimate scientific research. The truth is that we simply don't know enough about the physics involved to make definitive judgments about what's natural and what might be artificial. The electromagnetic interactions between massive cometary comas and heliospheric plasma represent frontier science, where our theoretical understanding remains incomplete. What we can do is continue monitoring the situation with the most sophisticated instruments at our disposal, watching for patterns that might reveal the true nature of what we're observing. The next few weeks will provide data that could reshape our understanding of how the solar system operates as an interconnected electromagnetic environment. Whether that data supports natural explanations or points toward more exotic possibilities, it will contribute to our knowledge of phenomena that operate on scales far beyond anything we can replicate in terrestrial laboratories. The universe is conducting experiments that we're only beginning to learn how to observe and interpret. The question isn't whether directed energy effects are real, it's whether we're sophisticated enough to recognize them if they are. As 3I Atlas approaches its date with our Sun, we're about to get our most comprehensive look yet at plasma physics operating on truly cosmic scales. If what we see challenges our assumptions about what's possible in the natural universe, we'll need to be prepared to expand our understanding in ways that might make us fundamentally reconsider our place in the galaxy around us. Part 10. The October Nexus and the Unknown Danger. October 2025 is shaping up to be one of the most astronomically significant periods in recorded history, a convergence of celestial events that reads like something from an ancient apocalyptic text. But unlike the fevered imaginings of doomsday prophets, these are real astronomical phenomena, precisely calculable and scientifically verifiable. The question isn't whether they're happening, it's what they might mean for our planet and our understanding of how the solar system really works. The centerpiece of this cosmic convergence is the new moon on October 21st, when Earth's natural satellite will be positioned directly between our planet and the Sunday. This isn't unusual in itself. New moons occur monthly with clockwork precision, but this particular new moon coincides with several other significant astronomical alignments that create conditions we haven't seen in recorded history. 3I Atlas reaches perihelion on October 30th, its closest approach to the Sun at roughly 1.4 astronomical units. That's still well outside Earth's orbit, farther than Mars at its closest approach, but close enough for the object's massive coma to interact intensively with solar wind conditions that are growing increasingly turbulent as solar cycle 25 approaches its peak. Meanwhile, comet C/2025 R2 Swan makes its closest approach to Earth around October 19th through 21st, passing within just 0.26 astronomical units of our planet. That's roughly 1/4 the distance between Earth and the Sun, close enough for its developing tail to span several degrees of sky when viewed through binoculars. The timing creates what some researchers are calling a reset configuration, multiple astronomical bodies aligned in ways that haven't occurred since before the development of modern space weather monitoring. It's as if the universe is providing us with a natural experiment in cosmic electromagnetics, one designed to test theories about how celestial mechanics might influence terrestrial processes. But here's what makes this period particularly intriguing from a scientific standpoint. We're not just dealing with ordinary comets following predictable orbits. 3I Atlas carries chemistry and materials from another star system, potentially responding to solar heating in ways that no object in our local comet population ever has. Its massive carbon dioxide-rich coma represents uncharted territory in plasma physics, a structure that could interact with heliospheric conditions in completely unprecedented ways. The visibility situation presents both opportunities and challenges for ground-based observers. 3I Atlas itself will be on the far side of the Sun during most of October, making direct observation impossible from Earth's surface. But space-based telescopes continue monitoring the object's development, and its electromagnetic signature remains detectable through radio and X-ray observations that penetrate the solar glare. Comet Swan offers better viewing prospects for amateur astronomers, with its tail already extending roughly 2.5 degrees across the sky. That's about 5 times the width of the full moon, an impressive sight for anyone with access to dark skies and basic optical equipment. As it approaches closest approach, the tail may become visible to naked eye observers in locations free from light pollution. More significantly, both objects will be interacting with solar wind conditions that are increasingly dynamic as the Sun approaches solar maximum. Recent weeks have seen G3 geomagnetic storms, elevated solar flare activity, and the kind of coronal hole streams that create the electromagnetic vacuum conditions some researchers associate with earthquake triggering. The convergence of these factors creates what might be described as a natural stress test for theories about space weather effects on terrestrial processes. If electromagnetic coupling between heliospheric conditions and seismic activity is real, the October period should provide the most compelling evidence we've ever had access to. The global seismic monitoring community is watching this period with particular interest, not because they necessarily believe in space weather earthquake triggering, but because the sheer number of variables involved creates an unprecedented natural experiment. Multiple astronomical objects, enhanced solar activity, and a planet still adjusting to the massive stress changes from July's Kamchatka earthquake. It's a combination that should reveal something significant about how these systems interact. From a more speculative perspective, some researchers have proposed that the October alignment represents a kind of astronomical fresh start, a moment when celestial mechanics reset into new configurations that could influence everything from space weather patterns to the electromagnetic environment around Earth. The idea isn't based on established physics, but rather on pattern recognition from historical astronomical records. Looking at this symbolically rather than scientifically, the new moon of October 21st occurs in the constellation Virgo according to astronomical coordinates, though astrological traditions would place it in Libra due to the precession of Earth's axis over millennia. These symbolic frameworks don't influence physical processes, but they do provide cultural context that humans have used to interpret celestial events for thousands of years. The psychological impact of such convergences shouldn't be underestimated. When multiple dramatic astronomical events occur simultaneously, it creates a sense of cosmic significance that can influence human behavior in measurable ways. Financial markets, social movements, and individual decision-making all show statistical variations that correlate with periods of high astronomical drama. But let's return to the harder science. The debris trail hypothesis associated with 3I Atlas adds another layer of complexity to the October scenario. Some preliminary calculations suggest that Earth might encounter dust and particle streams from the object's passage sometime in 2026, creating potential meteor shower activity from interstellar materials. These encounters, if they occur, would provide our first opportunity to directly sample materials from another star system in terrestrial laboratories. The analysis of such particles could reveal details about stellar formation processes, interstellar chemistry, and the conditions that exist in the void between stars. However, it's crucial to emphasize that no official space agencies have confirmed hazardous debris encounters from 3I Atlas. The object's trajectory keeps it well away from Earth's orbital path, and its dust production appears to be following normal cometary patterns despite the unusual scale involved. The real unknown in all of this is how the various electromagnetic interactions will combine during the peak activity period. Solar wind conditions, multiple cometary plasma environments, and Earth's own magnetospheric dynamics create a three-body problem in space physics that's impossible to solve analytically. Computer models can provide estimates, but the actual behavior will only be revealed through observation. The October 30th perihelion passage represents the climax of 3I Atlas's visibility to space-based instruments. As the object rounds the Sun at its closest approach, solar heating will vaporize surface ices at maximum rates, potentially expanding the coma to dimensions that exceed the Sun's own diameter. The spectroscopic opportunities during this period are unprecedented. Every major space telescope capable of solar observations will be focused on 3I Atlas, gathering data about interstellar chemistry, plasma interactions, and electromagnetic field structures that we've never been able to study before. Ground-based radio telescopes will monitor electromagnetic emissions from the interaction region, while X-ray observatories track high-energy processes in the coma's ionized components. The data collected during this period will likely keep plasma physicists busy for years trying to understand what they've observed. From Earth's perspective, the key question is whether any of this astronomical drama will translate into measurable effects on terrestrial systems. The earthquake correlations we've been exploring, the electromagnetic anomalies associated with geomagnetic storms, and the various theories about space weather triggering all face their most significant test during the October convergence. If space weather effects on seismic activity are real, this period should provide clear evidence. If they're not, the absence of correlations during such an astronomically active time would effectively put the hypothesis to rest. Either way, we're about to get definitive answers to questions that have been debated for decades. The unknown danger isn't necessarily that something catastrophic will happen, it's that we might discover our understanding of how the solar system works is far more incomplete than we've realized. The universe is about to conduct an experiment in cosmic physics on a scale we've never witnessed before. Whether we're prepared to understand the results remains an open question. But ready or not, October 2025 is going to reshape our knowledge of the electromagnetic environment we inhabit and our place within the larger cosmic community. The convergence is coming, and with it, answers to questions we've only recently learned how to ask. Part 11. The Full Comet Swarm. If you thought 3I Atlas was travelling alone through this cosmic theatre, prepare to have your perspective dramatically expanded. The final months of 2025 are witnessing what astronomers are calling a comet swarm, 7 distinct objects converging on the inner solar system simultaneously, creating the most crowded and scientifically rich period for comet observation in living memory. Let's meet the full cast of this celestial drama, each bringing its own unique characteristics and scientific mysteries to the performance. First, our headline act, 3I Atlas, the interstellar heavyweight with its massive carbon dioxide coma spanning half the Sun's diameter. Perihelion on October 30th at 1.4 astronomical units, closest Earth, to approach at 1.8 astronomical units. This alien visitor continues to defy conventional cometary physics, maintaining activity at distances where most comets remain dormant. Then we have C/2025 R2 Swan, perhaps the most visually spectacular member of our ensemble. Making its closest approach to Earth around October 19th through 21st at just 0.26 astronomical units, this comet has already developed a tail extending 2.5 degrees across the sky. That's 5 full moon widths of ghostly gas and dust, visible through binoculars and potentially naked eye observable from dark sky locations. C/2025. A 6 lemon represents our rapidly evolving surprise. Initial brightness forecasts suggested a modest performance, but recent observations show the object brightening much faster than predicted. Current models suggest it could reach 4th magnitude by late October, bright enough for naked eye visibility under reasonably dark skies. Lemon's rapid evolution makes it a favourite among amateur astronomers tracking its development night by night. C/2025 K1 Atlas, not to be confused with our interstellar visitor, reached perihelion on October 8th. This more conventional comet provided early autumn viewing opportunities before the main October convergence, serving as something of a warm-up act for the celestial spectacular to follow. 210 P/Christensen enters the stage in early November, representing the periodic comet category in our lineup. Unlike the long-period visitors making their first recorded appearances, Christensen follows a predictable orbit that brings it back to the inner solar system every few years. This familiarity makes it an ideal comparison object for studying the unusual behaviours of our interstellar and long-period visitors. 24 P/Schaumass extends the performance into late 2025 and early 2020. 6 providing continuity as the main October convergence disperses. This periodic comet's extended visibility offers opportunities to study how different objects respond to varying solar wind conditions as solar cycle 25 progresses. Finally, we should acknowledge C/2024 G3 Atlas, an earlier 2025 performer that provided stunning sun-grazing observations before our current ensemble assembled. While no longer active, its earlier passage established baseline measurements for space weather interactions that help interpret the current convergence. The mechanics of comet tail development provide crucial context for understanding what we're observing. Comets actually develop two distinct types of tails through completely different physical processes, and the interplay between them reveals details about both the objects themselves and the space environment they're traversing. Dust tails form through the simple process of solar radiation pressure. As sunlight strikes tiny particles liberated from the comet's nucleus, photons transfer momentum, slowly accelerating the dust away from the comet. Larger particles respond less to this pressure than smaller ones, creating the characteristic curved appearance as different-sized particles follow slightly different trajectories. Ion tails operate through electromagnetic rather than radiation pressure effects. When high-energy photons from the Sun ionize neutral atoms and molecules in the comet's coma, they create charged particles that immediately respond to magnetic field lines in the solar wind. These ions get swept away from the comet at tremendous velocities, creating the straight, blue-colored tails that always point directly away from the Sun, regardless of the comet's orbital motion. The distinction becomes crucial when multiple comets are active simultaneously in varying solar wind conditions. Each object samples a slightly different electromagnetic environment, creating a natural laboratory for studying plasma physics across millions of cubic kilometers of space. During periods of enhanced solar activity, like the geomagnetic storms we've been experiencing, ion tail behavior becomes particularly dramatic. Coronal mass ejections can literally disconnect ion tails from their parent comets, a phenomenon spectacularly captured by spacecraft observations of comet Encke in 2007, when a solar eruption severed its plasma tail completely. The current solar cycle 25 maximum conditions make such disconnection events increasingly likely as our comet swarm approaches perihelion. Each object's response to space weather disturbances provides data about plasma density, magnetic field strength, and electromagnetic turbulence that would be impossible to gather through any other means. For amateur observers, the swarm offers unprecedented opportunities to witness comet evolution in real time. SWAN's impressive tail development provides binocular targets that change noticeably from night to night. Lemon's rapid brightening creates a moving target for photographers and visual observers tracking its development. Professional astronomy is equally excited by the scientific opportunities. The variety of composition, orbit types, and activity levels represented in the swarm provides natural control groups for studying cometary physics. Comparing how the interstellar visitor 3I Atlas behaves relative to solar system, natives like Christensen reveals fundamental differences in ice composition and outgassing characteristics. Space-based observatories are maximizing their comet observation time during this period. The James Webb Space Telescope has dedicated significant observing slots to spectroscopic analysis of the various objects, seeking to understand compositional differences and their implications for solar system formation processes. The Hubble Space Telescope continues its detailed monitoring of morphological changes in comet comas and tail development. Its high-resolution imaging capabilities reveal structural details in the gas and dust envelopes that ground-based observations cannot resolve. Radio telescopes monitor electromagnetic emissions from the ionized components of comet comas, while X-ray observatories track high-energy processes in the interaction regions between comet plasma and solar wind. The coordination between different wavelength observations provides comprehensive pictures of how these objects interact with their space environment. From a space weather perspective, the swarm creates multiple probe points throughout the inner solar system. Each comet's plasma environment responds to solar wind conditions in real time, providing distributed measurements of electromagnetic field strength, particle density, and magnetic turbulence across vast regions of space. The data being collected will likely reshape our understanding of heliospheric physics for years to come. Never before have we had so many natural plasma probes operating simultaneously during a period of high solar activity. The measurements they're providing reveal details about magnetic field structures, current systems, and electromagnetic wave propagation that were previously purely theoretical. But perhaps the most intriguing aspect of the swarm is what it reveals about the dynamic nature of our local cosmic environment. The solar system isn't a static collection of planets orbiting through empty space. It's a complex, interconnected electromagnetic system where objects from interstellar space can influence conditions throughout the heliosphere. The convergence of 7 distinct comets during solar cycle 25 maximum represents a natural experiment in cosmic physics that couldn't be replicated through any human technology. Each object contributes its own electromagnetic signature to the overall heliospheric environment, creating conditions that may influence everything, from space weather patterns to the space weather, subtle electromagnetic fields that surround our planet. As we move through the peak activity period in late October and November, ground-based observers will witness celestial mechanics in action on a scale rarely seen in human lifetimes. Multiple comets developing tails simultaneously, space weather disturbances, creating disconnection events, and the interplay between different plasma environments, all playing out against the backdrop of an increasingly active Sunday. The comet swarm of 2025 isn't just an astronomical curiosity, it's a window into the fundamental processes that govern how matter and energy behave in the space environment around our star. What we learn from these observations will influence our understanding of everything from planetary formation to the prospects for interstellar travel. The show is just beginning, and the universe has reserved front-row seats for anyone willing to look up and pay attention to the cosmic drama unfolding overhead. Part 12. The Energy Tsunami. There's an invisible storm building around our planet, one that makes the most powerful hurricanes look like gentle breezes by comparison. As solar cycle 25 reaches its crescendo, our sun is unleashing electromagnetic fury on a scale that occurs only once every 11 years, and sometimes much longer. What we're witnessing isn't just increased solar activity, it's a fundamental restructuring of the electromagnetic environment that surrounds and protects our world. The numbers tell a story that would be terrifying if it weren't so fascinating. Sunspot numbers have climbed steadily throughout 2024 and 2025, reaching levels that exceed many forecasters' predictions. The Solar Dynamics Observatory captures images daily of our star's surface, writhing with magnetic complexity, vast regions where field lines twist and tangle until they snap with explosive violence. Each solar flare releases energy equivalent to billions of nuclear weapons detonated simultaneously. The largest X-class events hurl charged particles and electromagnetic radiation across the solar system at nearly the speed of light, creating conditions in Earth's magnetosphere that can persist for days or weeks after the initial explosion. But it's not just the dramatic eruptions that define solar maximum. The entire character of our star changes during these peak activity periods. The solar wind becomes more variable, switching between high-speed streams from coronal holes and slower, denser material from active regions. The heliospheric current sheet, that vast spiral of electric current extending from the sun's equator, becomes more warped and complex, creating pockets of electromagnetic turbulence throughout the inner solar system. This is the environment that 3I Atlas and the comet swarm are encountering as they approach their closest encounters with our star. Instead of the relatively quiet, predictable space weather conditions that characterize solar minimum, they're sampling a heliosphere in full electromagnetic fury. The historical perspective adds weight to what we're observing. Solar cycle 25 represents the first solar maximum since the development of truly comprehensive space weather monitoring. Previous cycles were tracked through sunspot counts and ground-based magnetic measurements, but we now have satellites throughout the solar system, providing real-time data about conditions that were previously invisible to human observation. The Parker Solar Probe has ventured closer to the Sun than any human-made object in history, sampling the solar wind directly from its source and revealing magnetic field structures that challenge theoretical models. The Solar Orbiter mission provides coordinated observations from different vantage points, creating three-dimensional maps of solar wind evolution as it propagates throughout the heliosphere. This enhanced monitoring capability means we're seeing details of solar maximum that no previous generation could observe. The complexity is staggering. Magnetic field lines that reconnect and reconfigure on timescales of minutes, particle acceleration processes that boost solar wind velocities to over 700 kilometers per second, and electromagnetic wave phenomena that propagate across astronomical distances. When these conditions encounter Earth's magnetosphere, the results can be spectacular and sometimes problematic. The geomagnetic storms we've experienced throughout 2025 have produced aurora displays visible as far south as the Carolinas, while simultaneously disrupting GPS navigation systems and causing minor power grid fluctuations. The G4 severe storm of early 2025 demonstrated just how vulnerable our technological infrastructure has become to space weather effects. Airlines rerouted polar flights to avoid radio blackouts, while utilities from Canada to Texas reported elevated induced current levels in their transmission systems. But here's what makes the current situation particularly noteworthy. We're not just dealing with normal solar maximum conditions. The convergence of multiple comets, led by an interstellar visitor with an unprecedented electromagnetic footprint, is creating space weather scenarios that have no historical precedent. Each comet in the swarm acts as a plasma probe, sampling and responding to solar wind conditions in real time. Their massive comas create interaction regions where electromagnetic fields can be amplified, focused, or modified in ways that aren't yet fully understood. The combined effect is like having multiple tuning forks resonating simultaneously in a cosmic echo chamber. The traditional view of space weather treats it as a one-way interaction. The sun affects everything else in the solar system through electromagnetic radiation and particle streams. But the presence of massive cometary plasma structures suggests a more complex reality where objects in the heliosphere can influence space weather conditions through feedback mechanisms. 3I Atlas, with its coma spanning hundreds of thousands of kilometers, represents a particularly significant perturbation in the local electromagnetic environment. Its interaction with solar wind creates bow shocks, magnetic field deflections, and particle acceleration processes that extend far beyond the visible coma boundaries. When multiple such objects operate simultaneously in an already turbulent heliospheric environment, the cumulative effects could theoretically influence space weather patterns throughout the inner solar system. This isn't established science. It's frontier research that pushes the boundaries of our understanding about how electromagnetic systems behave on cosmic scales. The cultural and psychological dimensions of this electromagnetic storm deserve consideration as well. Throughout human history, periods of unusual celestial activity have coincided with significant social and political changes. The correlation doesn't imply causation, but it reflects the deep connection between cosmic rhythms and human consciousness that cultures worldwide have recognized for millennia. The current convergence of solar maximum, multiple comets, and global social tensions creates conditions that seem almost scripted for historical significance. Whether this represents meaningful synchronicity or simple coincidence depends largely on your perspective about how cosmic and terrestrial systems might be interconnected. From a purely physical standpoint, solar activity does influence Earth's electromagnetic environment in measurable ways. The global electric circuit, the system of currents flowing between the ionosphere and Earth's surface, responds to space weather variations with changes that can be detected by sensitive instruments worldwide. Some researchers have proposed that these electromagnetic variations might influence biological systems, from bacterial behavior to human neurological function. The mechanisms remain speculative, but laboratory studies have demonstrated that organisms can respond to electromagnetic field changes at levels comparable to those produced by geomagnetic storms. If such effects exist, periods of intense solar activity, like the current cycle maximum, could theoretically influence everything, from mood and cognitive function to social behavior and decision-making processes. The idea remains on the fringes of mainstream science, but it suggests possible pathways through which cosmic events might influence terrestrial affairs. The energy tsunami metaphor becomes particularly apt when you consider the power levels involved. The total electromagnetic energy contained in a severe geomagnetic storm exceeds the electrical consumption of human civilization by several orders of magnitude. This energy doesn't just dissipate harmlessly, it interacts with every conductive system on and around our planet. Power grids experience induced currents that can damage transformers and trigger cascading failures. Pipeline networks see elevated corrosion rates as telluric currents flow through buried infrastructure. Even the human nervous system, with its network of bioelectrical signals, exists within this invisible ocean of electromagnetic energy. As we approach the peak convergence period in late October, the intensity of these interactions will almost certainly increase. Solar activity typically remains elevated for months around solar maximum, while the comet swarm will be at peak activity levels as objects reach perihelion and develop maximum coma and tail development. The combination creates what might be described as a perfect storm in space weather, multiple electromagnetic sources operating simultaneously in an environment already charged with solar maximum energy. The effects could range from enhanced aurora displays and improved scientific observations to more serious disruptions of technological systems and infrastructure. What we're witnessing represents more than just an interesting astronomical period. It's a stress test of the electromagnetic systems that govern everything from Earth's magnetic field to the technology that supports modern civilization. The results will shape our understanding of how these systems interact and how vulnerable we might be to future space weather events. The energy tsunami is building, driven by forces that operate on scales far beyond human control or influence. Our role is to observe, measure, and try to understand what these cosmic energies might mean for our planet and our place within the larger electromagnetic symphony of the solar system. Whether you interpret this as ominous warning or unprecedented opportunity depends on your perspective about humanity's relationship with the cosmos. But one thing is certain, we're about to experience space weather conditions that no previous generation has ever witnessed, and the data we collect will influence our understanding of these phenomena for decades to come. Part 3. Modern Chaos. The universe has always had a peculiar sense of timing, but September 10th, 2025, pushed the boundaries of what rational minds can dismiss as mere coincidence. At precisely 11:27 a.m. Mountain Daylight Time, seismometers across Utah's Wasatch Fault Zone registered a magnitude 4.1 earthquake. The tremor centered 15 kilometers southeast of Salt Lake City, shallow at just 6 kilometers deep, fitting perfectly within the normal parameters for a region where tectonic stress builds like pressure in a kettle. But here's where rational explanation meets uncomfortable timing. Less than 4 hours after the ground shook, the same state witnessed something that sent shockwaves through an already fractured political climate, an assassination attempt on a controversial figure during a public event. The shooter was apprehended quickly, but the event carved another fault line through a society that seems increasingly prone to extremes. 2 events, same day, same state, no obvious connection except the tyranny of the clock and the coincidence of geography. Yet when you're investigating patterns of synchronicity during periods of heightened electromagnetic activity, even the most skeptical observer begins to wonder if there might be deeper currents flowing beneath the surface of apparent randomness. The earthquake itself was nothing extraordinary by Utah standards. The Wasatch Fault system has been generating similar tremors for millennia, driven by the ongoing extension of the Basin and Range Province as North America's western edge continues its complex geological dance. Magnitude 4 earthquakes occur roughly every few months in this region, posing no unusual seismic concerns to local authorities or residents. But timing, as they say, is everything. September 10th fell within a period of elevated geomagnetic activity following the G3 storm that had swept through Earth's magnetosphere just days earlier. Solar wind conditions remained disturbed, with recurring high-speed streams from persistent coronal holes creating ongoing electromagnetic turbulence in the space around our planet. Meanwhile, the political incident occurred against a backdrop of social tensions that have been building throughout 2025. Polarization metrics, scientific measures of how divided public opinion has become on key issues, have reached levels not seen since the American Civil War era. The attempted assassination represented just the latest in a series of violent incidents that seem to reflect deeper currents of instability running through contemporary society. From a purely statistical standpoint, the simultaneous occurrence of an earthquake and a politically significant event in the same geographical region proves absolutely nothing about causal relationships. Utah experiences regular seismic activity due to its tectonic setting, while political violence has become disturbingly common across the United States in recent years. Finding temporal correlations between such events becomes almost inevitable when you're actively looking for patterns in the data. But pattern recognition is exactly what makes the human brain so remarkably effective at navigating complex environments, and so prone to seeing connections that may not actually exist. When two dramatic events occur in close temporal and geographical proximity during a period when space weather conditions are elevated, our cognitive systems naturally seek explanations that link them together in meaningful ways. The challenge lies in distinguishing meaningful correlations from statistical artifacts. Earthquake catalogues contain thousands of events annually, while political tensions create hundreds of significant incidents throughout any given year. The opportunities for apparent synchronicity become enormous, even if no real connections exist between these seemingly separate phenomena. However, some researchers who study electromagnetic effects on biological and social systems suggest that periods of enhanced space weather might indeed influence both geological and social processes through related mechanisms. Geomagnetic storms can affect neural function in sensitive individuals, while the same electromagnetic disturbances might theoretically influence the subtle stress fields that control earthquake timing along fault systems. The proposed mechanisms remain highly speculative and controversial within the scientific community. Changes in the global electric circuit could theoretically alter neural firing patterns in ways that influence mood, decision-making, and social behavior. The same electromagnetic variations might also affect the electrochemical processes that influence rock strength and pore fluid pressure along active fault systems. If such effects exist, they would likely be subtle, nudging systems that are already close to critical points, rather than creating entirely new behaviors. A politically motivated individual might be slightly more likely to act during periods of electromagnetic disturbance, while a fault system under tectonic stress might be marginally more prone to failure when space weather conditions align in specific ways. The Utah events illustrate the profound challenge of investigating such possibilities scientifically. Both the earthquake and the political incident occurred in contexts where they were already statistically likely to happen. The Wasatch Fault generates regular seismic activity due to its geological setting, while the current political climate has unfortunately made violence increasingly common across multiple states. What's less controversial is the demonstrable impact of space weather on technological systems that increasingly mediate human social interactions. Geomagnetic storms can disrupt GPS navigation signals, interfere with satellite communications networks, and create power grid instabilities that affect everything from financial markets to social media platforms. During periods of elevated solar activity, these technological disruptions can cascade through interconnected systems in ways that amplify existing social tensions. Trading algorithms may behave erratically when GPS timing signals are degraded by space weather effects. Emergency communication systems might fail precisely when they're most needed during crisis periods. Social media platforms could experience outages that prevent the normal flow of information during times of heightened social stress. The September events occurred during such a period of elevated electromagnetic activity. While the specific impacts on technological systems were relatively minor, the cumulative effect of multiple small disruptions could theoretically contribute to the kind of heightened social stress that makes dramatic events statistically more likely to occur. Beyond Utah, similar patterns of apparent synchronicity have emerged throughout 2025 in various locations worldwide. Unusual seismic activity has coincided with social unrest in several regions, while periods of intense space weather have correlated with spikes in various measures of social tension and political instability. The global protest movements that erupted during the G3 storm period provide another compelling example. While the underlying social grievances existed long before the space weather event, The timing of widespread demonstrations across multiple continents during days of intense geomagnetic activity suggests possible connections that warrant careful scientific investigation. But here's the crucial question. Are we witnessing genuine correlations between cosmic and terrestrial events, or simply falling victim to the natural human tendency to find patterns in random data? During periods of high astronomical drama, like the current comet convergence and solar maximum, we become more sensitive to coincidences and more likely to interpret them as meaningful rather than random. As we approach the October convergence period, when multiple astronomical factors align during peak solar activity, we should expect more such apparent synchronicities to emerge from the chaos of daily events. The key challenge lies in maintaining the delicate balance between healthy skepticism and openness to possibilities that might challenge our conventional understanding of how cosmic and terrestrial systems interact. Part 14. Archetypal Shift, Death, Rebirth, and Radical Responsibility. Something profound shifts in the collective human psyche when the sky begins to dance with unusual activity. Throughout history, periods of intense celestial drama have coincided with fundamental transformations in how societies understand themselves and their place in the cosmos. The convergence we're witnessing in late 2025 carries all the archetypal hallmarks of such transformational moments, death of old patterns, birth of new possibilities, and the uncomfortable space between where radical responsibility becomes our only compass. October 21st, 2025 marks a new moon that astronomers calculate with mathematical precision, but which carries symbolic weight that transcends mere celestial mechanics. This lunar reset occurs precisely when multiple cosmic actors converge in what could be described as a celestial symphony of renewal. The timing feels almost orchestrated by some cosmic intelligence, though science would caution us against attributing intentionality to what might simply be remarkable coincidence. The archetypal language of death and rebirth permeates human cultures precisely because it reflects patterns we observe repeatedly in natural cycles. Seeds must decompose before they can sprout. Forest fires clear undergrowth to enable new growth. Individual cells must die for organisms to renew themselves. These patterns operate on scales from the microscopic to the galactic, suggesting universal principles that govern transformation processes throughout nature. In the symbolic framework that many cultures associate with cosmic events, the constellation Virgo traditionally represents harvesting, discernment, and the careful preparation required for new beginnings. Astronomically speaking, the actual boundaries of constellations differ significantly from their astrological counterparts, but the archetypal symbolism points toward themes of purification and renewal that seem remarkably appropriate for our current moment. What makes this period particularly significant is not just the celestial events themselves, but the context in which they occur. Humanity finds itself at a crossroads where multiple crises converge: environmental challenges, technological disruption, social fragmentation, and the persistent question of whether our species can evolve beyond its current limitations before those limitations prove catastrophic. The concept of radical responsibility emerges naturally from such moments of convergence. When external circumstances become chaotic and unpredictable, the only reliable constant becomes our capacity to choose how we respond to whatever emerges. This isn't about controlling outcomes, which remains largely beyond individual capability, but about taking full ownership of our responses to uncontrollable circumstances. Radical responsibility means abandoning the comfortable fiction that we're passive victims of external events. It requires acknowledging that our perceptions, interpretations, and responses to circumstances are choices we make moment by moment, even when those choices feel automatic or predetermined. This shift from reactive to responsive consciousness represents perhaps the most significant evolution available to individual human beings. The shadow integration process becomes particularly relevant during periods of collective stress and polarization. When societies fragment into opposing camps, each side tends to project its own unacknowledged darkness onto the opposition, creating cycles of mutual demonization that make genuine communication increasingly difficult. The cosmic convergence offers an opportunity to recognize these projection dynamics and reclaim the shadow material we've disowned. Shadow work isn't pleasant or comfortable. It requires acknowledging the parts of ourselves that we'd prefer to deny or ignore, the capacity for selfishness, cruelty, ignorance, and destruction that exists within every human being. But until we acknowledge these potentials within ourselves, we remain vulnerable to acting them out unconsciously while righteously condemning their expression in others. The polarization we observe in contemporary society reflects this collective shadow projection process, operating on a massive scale. Political opponents become demonic caricatures rather than fellow human beings with different perspectives and priorities. Social media algorithms amplify these dynamics by creating echo chambers that reinforce existing beliefs while demonizing alternative viewpoints. Breaking free from these patterns requires what some traditions call fierce compassion, the willingness to extend genuine understanding even toward those whose actions we find reprehensible. This doesn't mean condoning harmful behavior or abandoning appropriate boundaries, but rather recognizing the shared humanity that exists even in those who have lost their way. The love and forgiveness dimension of radical responsibility represents perhaps its most challenging aspect. Forgiveness, properly understood, isn't about excusing harmful behavior or pretending that injustices haven't occurred. Instead, it's about releasing the toxic burden of resentment that ultimately harms the forgiver more than the forgiven. It's about recognizing that holding on to anger and hatred only perpetuates the very cycles we claim to oppose. This forgiveness extends not only toward others, but perhaps most crucially toward ourselves. The perfectionist tendencies that drive much human suffering stem from the inability to accept our own limitations and mistakes. Radical responsibility includes accepting our own humanity, our capacity for error, growth, and transformation, without either self-condemnation or self-delusion. During periods of cosmic convergence like the current one, opportunities for consciousness evolution accelerate dramatically. The intensified electromagnetic environment may indeed influence neural function in subtle ways that make expanded awareness more accessible. The symbolic power of celestial events creates openings in collective consciousness that can facilitate breakthrough insights and transformational experiences. But these opportunities require active participation rather than passive waiting. The cosmic energies provide favorable conditions for growth, but individual choice and effort remain essential, components of any genuine transformation process. The universe may be offering invitations to evolve, but we must choose whether to accept those invitations and do the work they require. Practical integration of these principles begins with simple daily practices that cultivate awareness and responsibility. Meditation, or contemplative practices, help develop the capacity to observe our mental and emotional patterns without being completely identified with them. Journaling can illuminate unconscious assumptions and reactive patterns that normally operate below the threshold of awareness. Physical practices that connect us with natural rhythms, spending time outdoors, eating seasonally, adjusting sleep patterns to match lunar cycles, can help attune individual consciousness to larger cosmic patterns. These aren't mystical requirements, but practical ways of remembering our embeddedness within larger natural systems. Community engagement provides essential grounding for archetypal transformation processes. Individual insight without collective expression often remains abstract and ineffective. Finding ways to contribute meaningfully to community well-being, whether through volunteer service, artistic expression, or simply showing up authentically in relationships, helps integrate transformational insights into practical reality. The death-rebirth cycle requires releasing attachments to identities and patterns that no longer serve our highest potential. This might mean letting go of career identities that have become constraining, relationship patterns that perpetuate unconscious dynamics, or belief systems that limit our capacity for growth and service. As October 21st approaches, followed by the peak convergence period when 3I Atlas reaches perihelion, the archetypal invitation becomes increasingly clear. The old ways of being human, characterized by unconscious reactivity, shadow projection, and victimhood consciousness, are proving inadequate to meet current challenges. The cosmic convergence offers powerful symbolic support for choosing conscious evolution instead, but transformation remains ultimately a choice that each individual must make for themselves. The universe may provide favorable conditions and symbolic encouragement, but the actual work of consciousness evolution requires courage, commitment, and radical honesty about who we've been and who we might become, the question that confronts us isn't whether cosmic events influence human consciousness, but whether we have the wisdom and courage to respond to whatever influences exist in ways that serve the highest good of all life on Earth. Part 15. Conclusion. The Cosmic Journey and Manifestation. Here we stand at the threshold of November 2025, having witnessed one of the most astronomically dramatic periods in modern history. The facts are indisputable. Our Sun has awakened from its slumber with solar cycle 25 reaching unprecedented activity levels. Multiple comets, including the third confirmed interstellar visitor, 3I Atlas, have painted the heavens with their ethereal brushstrokes of plasma and dust. Earth has responded with seismic punctuation marks, from Kamchatka's massive magnitude 8.8 earthquake to the continuing aftershock sequences that remind us of the profound forces operating beneath our feet. But as our investigation draws to a close, we find ourselves confronting a more fundamental question than whether these events are causally connected. We're forced to examine how we process information during periods of cosmic intensity and what that reveals about human consciousness itself. The universe appears to be conducting experiments not just in astrophysics and geophysics, but in the very nature of awareness and meaning-making. The spectrum of possibilities we've explored ranges from established scientific fact to the wildest speculative fiction. Solar cycle 25 is demonstrably more active than forecasters predicted, producing G4 class geomagnetic storms that have disrupted technological systems and painted aurora displays across latitudes far from their usual polar domains. The comet roster we've tracked, from 3I Atlas, with its massive coma spanning half the Sun's diameter, to Swan's impressive tail visible to binocular observers, represents genuine astronomical phenomena documented by institutions from NASA to the European Space Agency. The earthquake sequences in Kamchatka, Utah, and other seismically active regions have been precisely measured by networks of sensitive instruments that leave no doubt about their occurrence or magnitude. The timing correlations with space weather events, while intriguing, remain in the realm of statistical curiosity rather than established causation. Science demands higher standards of evidence than temporal coincidence, no matter how compelling the patterns might appear. Yet even as we maintain appropriate skepticism about causal relationships, something profound has emerged from our investigation that transcends the specific claims we've examined. The process of tracking these correlations has revealed how human consciousness responds to periods of cosmic drama, and why such periods have historically coincided with significant cultural and social transformations. During times of celestial intensity, our pattern recognition systems become hyperactive, scanning for connections and meanings that might normally escape our attention. This heightened sensitivity isn't necessarily a flaw in human cognition. Throughout our evolutionary history, periods of environmental stress have been precisely when careful attention to subtle correlations provided survival advantages. Our brains may be naturally calibrated to detect meaningful patterns during periods of cosmic activity, because such patterns have historically been significant for our ancestors. The challenge in our modern information-saturated environment is distinguishing signal from noise when our pattern detection systems are operating at maximum sensitivity. The constant flow of data from global communication networks means we're aware of far more simultaneous events than any previous generation. The opportunities for apparent synchronicity multiply exponentially when you're tracking earthquake databases, space weather indices, political developments, and astronomical observations in real time. This represents both an unprecedented opportunity and a significant danger. The opportunity lies in our capacity to observe correlations across multiple domains with remarkable precision and scope. Never before have human beings possessed such detailed, real-time information about conditions throughout the solar system, tectonic processes across the planet, and social dynamics worldwide. If meaningful connections exist between cosmic and terrestrial processes, we're better positioned than any previous generation to detect and understand them. The danger lies in our susceptibility to information overload and pattern matching errors during periods of heightened sensitivity. When everything seems connected to everything else, genuine insights become indistinguishable from elaborate coincidences. The human brain's remarkable capacity for finding patterns can become a liability when those patterns are projected onto random or weakly correlated datasets. But perhaps the most significant insight from our investigation concerns the relationship between cosmic events and human creativity. Historical analysis reveals that periods of intense astronomical activity have consistently coincided with breakthrough innovations in art, science, philosophy, and technology. Whether this reflects causal influence or simply the inspirational power of dramatic celestial displays, the correlation suggests that cosmic convergences like the current one offer unique opportunities for expanded awareness and creative expression. Solar maximum periods, in particular, seem to correlate with increased human creativity and innovation across multiple domains. The enhanced electromagnetic environment might indeed influence neural function in subtle ways that facilitate breakthrough insights and novel connections between previously unrelated concepts. Alternatively, the symbolic power of cosmic drama might simply provide psychological permission for thinking outside conventional boundaries. Either way, the practical implications remain the same. Periods like the current convergence offer optimal conditions for creative projects, learning endeavors, and consciousness expansion practices. The elevated electromagnetic environment, whether through direct biological effects or symbolic inspiration, appears to facilitate the kind of non-linear thinking that generates genuine innovation and insight. For viewers who have followed our investigation from the beginning, the question now becomes how to integrate these insights into practical daily experience. The cosmic convergence of late 2025 offers a unique laboratory for experimenting with expanded awareness, but the principles we've explored remain relevant long after 3I Atlas completes its solar encounter and the comet swarm disperses throughout the outer solar system. Practical integration begins with developing reliable sources for tracking the phenomena we've discussed. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center provides real-time monitoring of solar activity and geomagnetic conditions. The United States Geological Survey maintains comprehensive earthquake databases with immediate alert capabilities. Astronomical software and websites offer detailed tracking information for comets, planetary positions, and other celestial events. But information without discernment becomes mere entertainment or anxiety fuel. The key lies in developing the capacity to process cosmic information in ways that enhance rather than overwhelm consciousness. This requires cultivating what might be called cosmic perspective, the ability to maintain awareness of larger patterns and cycles while remaining grounded in immediate practical responsibilities. Cosmic perspective includes recognizing that we're embedded within multiple cycles, operating on vastly different timescales. The 11-year solar cycle represents just one rhythm in a symphony that includes lunar months, seasonal variations, planetary orbital periods, and galactic rotations spanning hundreds of millions of years. Our brief human lifespans offer only tiny glimpses of these larger patterns, but even partial awareness can provide profound insights into our place within the cosmic order. The manifestation principles that emerge from this investigation aren't about magical thinking or wishful manifestation. They're about recognizing the enhanced creative potential that becomes available during periods of cosmic intensity and learning to channel that potential constructively. Solar maximum periods appear to amplify both positive and negative manifestation tendencies, making conscious direction of creative energy particularly important. This means paying careful attention to mental and emotional states during periods of elevated space weather activity. Negative thought patterns and emotional reactivity can manifest with unusual intensity when cosmic conditions are amplified. Conversely, positive intentions and constructive projects may receive unexpected support and acceleration during such periods. As we look toward the completion of solar cycle 25 and the gradual dispersal of the comet swarm throughout the outer solar system, the lessons of this investigation extend far beyond the specific events we've tracked. We've learned something crucial about the relationship between cosmic rhythms and human consciousness, between celestial mechanics and terrestrial creativity, between scientific skepticism and spiritual curiosity. The universe has offered us a remarkable demonstration of its creative power through the convergence of late 2025. How we integrate the insights from this demonstration will determine not only our capacity to understand future cosmic events, but our ability to participate consciously in the ongoing evolution of planetary consciousness itself. When the sky changes, we change. The cosmic journey continues, and our role as conscious observers becomes ever more crucial to the unfolding story of life in the universe.